Welcome to the Learning C++ by Creating Games in Unreal Engine 4 video course by Pax Publishing. My name is Nicholas Hellish. I've been programming for 4 years in C# and C++ using Unreal Engine 4 and Unity, and 7 years in game development using contract work, game jams, and other types of projects. I've learned how to code and program through a mix of self-taught and formal education under a master's level experienced programmer for games. This is the first video in the course where we're going to go over what we're going to explore in Unreal Engine 4 using C++. First, before we start, there are some prerequisites that are needed to help you succeed in this course. This course is tailored for working on a Windows machine or a computer with a Windows 7, 8, or 10 operating system. It is not tailored explicitly or required explicitly, but if you are working on a Linux or Macintosh machine, this may hinder you in the learning process. Then if you are familiar with Unreal's blueprint system, then it will help you understand this course better, but it is also not required. The main requirement is that you have a basic understanding of how to code, such as ending a line of code with a semicolon, when and where to place brackets, and so on, basic formatting. Now for what this course will cover. In the first section, we will be installing Visual Studio in Unreal Engine 4, and then covering the basics of C++ and how it is fundamentally working. Then in Section 2, we will be learning about Unreal Engine's code base and API, and then start building our level to test our code in. In Section 3, we will be creating the player's character code and adding a HUD element for our player. In Section 4, we will be creating gameplay elements such as explosive barrels, pickups, and a respawning system. In Section 5, we will be creating our menus so that the player can start a main menu and transition to our main level, as well as when the player dies, a death menu should show up and a pause menu for when we pause the game. In Section 6, we will finish up by creating an interaction system that allows us to press a button and something should happen to that specific object in front of us. And then we will finish up by packaging our project so we can use it outside of our project's window. The goals of this course will be to have familiarity with Unreal Engine C++ API and C++ in general, understanding the most used data types and functions to use within Unreal, and using that knowledge from this course to be able to implement Unreal's API into a true game development environment. And I hope to see you there. Welcome to Section 1, Setting up Visual Studio for Windows. In this video, we will be installing Visual Studio Community 2015 edition, downloading and installing Unreal Engine 4, and then exploring the Visual Studio interface afterwards. Let's start by installing Unreal Engine 4, because it will be faster than Visual Studio Community. Let's start by opening up our web page by going to this URL in our browser. This is the Unreal Engine web page. If you do not have an Epic Games login account, you will have to create one. If you do have one, simply select the top right where it will say login and then log into your account, and then select download. Download for Windows, and then once the installer has finished downloading into your computer, run the installer. This will be what the installer looks like when you run it initially. Select where you want it to download to, and then select install. It will ask for administration privileges. Select yes. Once it has finished installing, this will be the screen that shows up. You have to log into your Epic Games account again, and then afterwards we will be installing the Unreal Engine. Once you have logged into your account, go to Unreal Engine tab in the top left, select Library, Add Versions. It will automatically select the most recent version that it has been released for the public. If this is not the version that you have, select the arrow and it will show previous versions. For this course, we will be using 4.17.2. Select Install, and it will ask where to install it and the path. Select Options, and select Editor Symbols for debugging, and then scroll down, and uncheck iOS, Android, HTML5, and Linux, and then select Apply, as we will not be needing these for the course. Select Install, it will ask for administration privileges, select Yes, and then it will install to your computer. Once the engine has finished installing, if you would like to change these options you made when you started the installation, simply click the arrow next to the launch button and select Options. Unchecking something will uninstall it, and checking it will install it. Simply select Apply to apply these changes. Now that Unreal Engine 4 is finished installing, let's install Visual Studio. First, let's start by opening up our browser and typing in this select URL. Scroll down to 2015 and select Download. You will have to be logged in with a Microsoft or Visual Studio account to download the installer, otherwise you will have to create an account. Select EXE instead of DVD and select Download. Once the download is finished, run the EXE. This will show up as your EXE, which is the installer for Visual Studio Community 2015. Select Custom and select the path of which it will install. If you are not able to, then the installer will automatically select a place for you. Select Next, and we will be using Visual Studio 2015 Update 3, and in the programming languages we will select Visual C++, and in the Windows and web development we will not be using anything, so unselect that. In cross-platform mobile development we will select C#, Visual C++, and everything in Common Tools and Software Development Kits. In Common Tools we will select Visual Studio Extensibility Tools Update 3. Once you have selected everything, select Next. This is everything that you will have to have selected, and select Install. It will ask for administration privileges. Select Yes. This will take a while. Now that Visual Studio has finished installing all of the components, we will have to restart the computer for those components to process properly. Now that we have Visual Studio installed, let's open it. Visual Studio is a text editor that has some handy features such as IntelliSense, which helps coders write code more efficiently, and many ease of use features built into the IDE, or text editor. Let's explore the interface of Visual Studio. On the right is the Solution Explorer. This is what we will use to organize our project and open other code files without opening the Windows Explorer, all within Visual Studio. At the bottom is the output window. This will tell us whether or not our build was successful. Now let's modify Visual Studio. At the top we have a tab called Tools. Select that, go to the bottom and select Options. This will allow us to edit our environment. Let's change the color theme from blue to dark, as this is easier on our eyes and healthier, as this does not cause eye strain, compared to light and blue. Select OK to apply these changes. Now let's go back to Tools and go back to Options, and we're going to edit our text editor, C++. Select Text Editor, go to C, go to Scroll Bars, and change our behavior to Map Mode for vertical scroll bar, and let's leave it at Medium, and leave the Show Preview tooltip checked. Click OK to apply these changes. This will allow us to move more quickly on the same page with ease. Now that we have Visual Studio and Unreal Engine installed, along with setting up and learning a bit about Visual Studio's interface, in the next video we will be discussing C++ fundamentals. Welcome to Section 1, Understanding C++ Fundamentals Part 1, Variables and Methods/Functions. In this video we are going to learn about variables and variable types, methods/functions, classes and structs, and what the private, public, and protected keywords are. Variables are containers of data. A variable is a container that holds only specific types of data when it is declared. When declaring a variable, you must also declare a name for that variable. This is for the programmer to be able to keep track of what is going on. Variables can be editable at runtime, or they can be set to constant, which doesn't allow for it to change once it's been set. Some common default variable types are bools or booleans, which are true and false variables. They can also be 1 or 0, which is 1 being true and 0 equaling false. Floats and doubles are decimal numbers with low accuracy and high accuracy, and they can both be positive or negative. Ints are whole number integers that can be positive or negative. Chars, which are single characters, they can be a letter or a symbol or a number. And strings, which are a whole series of characters. They can also be classified as an array of chars. Arrays are containers in memory for variables. Arrays can hold one type of variable, but it can hold multiple variables of that type. Each variable added to the array is called an element. Arrays have indexes to keep track of where each variable is within memory. Arrays always start at 0 for the index counter, because the index is how many elements away it is from where the array starts, like an offset. As you can see in the graph on the right, the array holds 5 integers. Index 0 holds an integer value of 16, and this repeats through all of the indexes. Methods and functions are basically the same thing, but are different in semantics that are not important for this course. For the duration of this course, we will be using the word functions because this is what Unreal Engine 4 uses. Functions are chunks of code that you could use to repeatedly use that chunk of code without having to copy and paste it everywhere. They can also be used to return values such as floats, bools, and other variable types. In the example on the left, we have a function that is executing multiple lines of code and not returning any values. In the example on the right, we have a function that is calculating the player health and returning a float value that is meant to represent the player health amount. Game development uses a programming practice called object-oriented programming. Object-oriented programming is a programming practice where it uses containers called classes to hold variables, functions, and other types of data within them through the idea of inheritance. Inheritance is the idea that if I make a class and it holds some variables and functions, and then I make a child class that inherits from the parent class, then the child class should be able to use those variables and functions from the parent class. The public, private, and protected keywords control what gets inherited and what doesn't. Public, meaning any functions or variables are accessible by any class regardless of inheritance. Protected, meaning this variable or function can be used within the same hierarchy of inheritance. And private, which is specific for that single class and it cannot be accessed by any other class. That includes inheritance. By default, classes have variables and functions set to private and must be specified to be public or protected. Classes and structs are the two main types of data that game programmers use. Structs are mostly used for data containers compared to classes, which are used to both hold data and execute code. You can create a variable that uses the type struct or class, thus creating your own custom variable. Structs by default are public, while classes are private by default. This graph is to visually explain the idea of inheritance, starting with human as the base class, and each subclass has two variables, hair color and age. Age is set to protected, so it cannot be accessed by another class, but it can be changed internally. Hair color is set to public, so it can be accessed by another class and changed by anybody. As you may also see, Liz has a third variable named finger length, and this does not inherit down to John. This is because it is a private variable, which makes it special to the Liz class. Liz is also changing Sam's hair color to pink because the variable is public, thus allowing Liz to change Sam's value regardless of inheritance. In the next video, we will be continuing with understanding C++ fundamentals by going over pointers and memory management. Welcome to Section 1, Understanding C++ Fundamentals Part 2, Pointers and Memory Management. In this video, we are going to learn about pointers and memory management concepts. Computers use memory to store data, and to execute code and to function just in general. Computers also use RAM, or random access memory sticks, to handle all of this memory. The smallest measured size of memory is 1 bit, or a single binary digit, which can be 0 or 1. On the right is a list of the different units of measurement for computer memory, starting at 1 bit and ending with GOP byte as the largest established unit of measurement for memory. Variables use data at different sizes that the RAM will automatically place into empty spaces in memory, depending on how much memory the program is allowed to use. An example would be, say here's our memory. Our memory has 10 bytes of available space, and now let's say we have a game that takes up 7 bytes of memory. So now we have 3 bytes of available memory left, but if we didn't have 7 bytes of memory, the game would crash due to memory overload. On the right is a graph representing the amount of space that these common variables use up on both 32-bit and 64-bit machines. You may notice that for chars and bools, there is no change. This is due to them being in exact values. The reason for why 64-bit machines use more memory than 32-bit machines is because they are given more precision and accuracy for the results of these variables, thus requiring more memory. Strings are not taken into account for this graph due to them being an array of chars and thus can range in size. Each location in memory has an address that is read typically with a 0x and then a bunch of seemingly random numbers and letters that will actually translate into binary. This is a beginner course, so we will not be learning how to convert hexadecimal, but it is important to understand that this is an address in memory. RAM will automatically segment out locations in memory for variables and other data. An example would be, say here's our memory, which each byte having its own location in memory. we have an integer that takes up 4 bytes of memory, and this integer is given its own address in memory based on the address it took up. This is all done by RAM automatically. Pointers are one of the most important features about C++ to understand. Pointers use a variable type that always takes up 4 bytes. Pointers are used to go to a location in memory or to get the actual address and can only point to one variable type when declared. When declared, if they are not set to an address, then they are immediately null pointers. An example would be, as shown, we have a player class instance, and you want to get the address of where that player instance is located in memory, so we would use a pointer to do so. The way you would declare that pointer is player class as the variable type, then a star, then a space, and then the name of the variable, so in this case, player class pointer. So why use pointers? Well, they are incredibly fast compared to direct references, and they allow us to pass data around at incredibly fast speeds. They allow for dynamic memory allocation, which is great for a game development environment, as we would need to spawn and despawn objects constantly in games, and having something that handles that is perfect for game developers. Dynamic memory allocation is a form of memory management that allows the programmer to request for more memory from the computer to use while the program is running. When using pointers, they allow for the program to request for an available space in memory that the pointer's variable type can hold while giving us an address automatically. They allow for us to dynamically load and unload content while the program is running, and thanks to advances in technology, we have a large amount of space to work in because of this. They are also known as garbage collectors, which take up pointers and other data which can no longer be needed and collects them up and deletes that data, which makes those spaces in memory available for use. An example would be, say we have a garbage can. This would be our representation of pointers and other data that has been marked for garbage collection. In this case, the garbage truck is the garbage collector picking up all of the data that has been marked for collection, and will be taken to be deleted and clear that space in memory or spaces in memory to be used again later on, or in the example of the garbage truck, taken away. In summary, for this course we have installed and set up Visual Studio and Unreal Engine 4, learned about variables and variable types, methods and /functions, classes and structs, what private, public, and protected keywords are, and what pointers and memory management in C++ are. In the next section, we will be understanding Unreal Engine 4. Welcome to Section 2, Understanding Unreal Engine 4. Video 1, Understanding the Unreal Engine's codebase and its naming conventions. In this video, we are going to learn about Unreal Engine's codebase, its naming conventions, and Epic's naming conventions. There are 4 main class types that build up the foundation of Unreal Engine's gameplay classes: UObject, AActor, which is a subclass of UObject, UActorComponent, which is also a subclass of UObject, and UStruct, which is Unreal's version of structs. UObjects are the base building block of the Unreal Engine. This class, coupled with UClass, which is an Unreal-specific way of determining if a class is Unreal-specific or not, provides a number of the most important base services in the engine. UObjects offer reflection of variables and functions, serialization of variables, which shows values from C++ in the editor that can be modified, garbage collection, which works in tandem with reflection, finding UObjects by name, configurable variables, and networking support for variables and functions. In most game engines that support object-oriented programming, this is very common to have a custom base class, and in the case of Unreal Engine, it's UObject. AActors or actors are an object that is meant to be part of the gameplay experience. In other words, this is the class or UObject that can be in the level by being either placed or created at runtime. All other objects can be in the level are extended or subclasses of actor. Actors have their own behavior, but they can also act as containers for a hierarchy for UActor components, also known as actor components. All actors by default have a single actor component that cannot be removed called the root component. Actors have a series of events that are called during the life cycle of the actor. First, they come into gameplay existence, which is usually when the actor is spawned, or the gameplay starts and the actor is already placed into the level. This is known as begin play. Tick will start to execute once per frame to do work over time, commonly known as update in other game engines, This also comes with a float variable named delta seconds, or commonly known as delta time. Delta time is the amount of time in milliseconds the previous frame took to complete. Tick is commonly used for frame rate dependent code, or to happen constantly, such as the player being able to look around. Finally is endplay, which executes when an actor is in the process of leaving the gameplay space. This usually occurs when the object or actor is destroyed. Actor components have their own behaviors and are usually responsible for functionality that is shared across many types of actors. For example, providing visual meshes, particle systems, camera perspectives, and physics interactions. While actors are often given high-level goals related to their role in the overall game, actor components usually perform the individual tasks that support those high-level goals. Actor components that have a transform, or also known as a location, a rotation, and scaling, which are all relative to their parent component or actor, are part of a subclass of actor components called U-scene components or scene components, which are also required to be the root component. A scene component can only attach to one parent component or actor, but it may also have children components attached to itself. As you can see in the image below, first-person character is our actor, and the root component of our actor is the capsule component. And that capsule component has many children components, which all inherit from scene component. You may also notice how character movement isn't attached to any other components. This is because it is an actor component, and they do not have transforms and thus cannot be attached to other components, but they can be attached to actors. U-structs do not extend from any particular class. To use a U-struct, you would create a normal C++ struct and mark it with U-struct, and the build tools will do the base work for you. Unlike a U-object, U-structs are not garbage collected. If you create dynamic instances of them, you must manage their lifecycle yourself. U-structs are meant to be plain old data types that have U-object reflections for editing within the Unreal Editor, blueprint manipulation, serialization, and networking, and so on. Unreal Engine provides tools that generate code for you during the build process, known as boilerplate. These tools have some class naming expectations and will trigger warnings or errors if the names do not match the expectations. The list of class prefixes delineates what the tools are expecting. Some of these you will not be able to know or need to know for this course, but are good to remember for the future. Epic Games, the creator and owner of Unreal Engine, is a game development company that has developed with the Unreal Engine since it was created and developed an asset naming system that they encourage users to use when starting out with the engine. This is so we can stay organized within our engine. We will try to obtain these naming conventions for this course. For the link to these naming conventions, it is placed at the bottom of the screen. In the next video, we will be explaining the Unreal Engine's codebase and the importance of planning scope. Welcome to Section 2, Video 2, explaining the Unreal Engine's codebase and the importance of planning scope. In this video, we are going to learn about Unreal Engine 4's codebase and how it's generally used, and understanding what is scope in planning ours. Blueprints are Unreal Engine 4's visual scripting language. I specified it as Unreal Engine 4 because it was introduced into the fourth iteration of the engine. It was originally designed as a programming language for non-programmers and designers, and this was originally intended to just add simple gameplay code. As Blueprint's popularity grew, Epic Games has been improving it to the point where you can make full games with it. Blueprints are fundamentally slower than C++, and this is because it is a high-level programming language, while C++ is a lower-level language. High-level scripting languages are typically simpler, easier to read, and learn and code in, but they are simpler and slower for the computer to process because it is converted from a language that's closer to human languages and into machine language by a compiler or interpreter, which takes time. Low-level scripting languages are more complicated in general, but they are faster for the computer to process. This is because it is typically closer to machine languages than human languages. This is also known as assembly languages. So let's say we have a ladder. We will call this ladder the ladder of code languages. At the bottom of the ladder is where we have the computer's CPU, where we execute the code. and every time we have code that we need to execute, we climb up the ladder to the coding language that we are using, and get the code that we intend to execute, and climb down to the CPU to execute that code. So, in the case of blueprints, we would have to climb higher, which takes longer than, say, C++, which is lower on the ladder, so it's faster to climb up and down the ladder than blueprints. One thing I want to stress is that if you program your games or applications correctly, you wouldn't really have the problem of code speed because it should be efficient, but you must understand the limitations of the language you are using. So why use blueprints if they are slower than C++? Well, for a game development environment, it's intended to be used as a sort of short-form implementation, or for quickly coding something specific and small. The usual format for using blueprints in a development environment is to build out the skeleton of the code in C++, and then in blueprints we would inherit from the C++ class, and then add slight modifiers and such. This would be useful for a pickup class made in C++. Then we would have a function for it when it is picked up, and in blueprint we would inherit from the pickup and name it health pickup. In C++, when the pickup function fires, we would tell it in blueprint to add health to the player. Scope is another way of planning out our project. In code, this would be known as coding within the curly braces. Any code that is outside the curly braces can also be known as global or out of scope depending on what you're doing. In project management for video games, this is commonly known as game design documents, or GDDs, that outline everything for the project. For this course, we will be scoping in a simple format, what the player can do, and any other features that we will add in to other objects in the world, as well as whether or not some code will be in C++ or Blueprint. So for the player, we will want to be able to walk around, jump, crouch, shoot a gun, have health, be able to die, and be able to interact with objects all within C++. We will want to be able to pause the game, but we will be using a combination of C++ and blueprints. Other objects within the world that we will have to code are game modes and level-ending actors that are only going to be coded in C++. We will be using the pause menu widget and set up the main menu and the main menu's level only within blueprints. And for pickups, the interaction system, destructible items, and the gameplay widget, we will be using a combination of C++ and blueprints. In the next video, we will be explaining Unreal Engine's garbage collection and its API. Welcome to Section 2, Video 3, explaining Unreal Engine's garbage collection and its API. In this video, we are going to learn about how Unreal Engine's garbage collection system works with its own API. Unreal Engine 4 uses its own implementation of automated garbage collection called Unreal Reflection System. These features are opt-in, meaning you have to add a specific markup or macro to our variable types. Otherwise, Unreal will ignore them and not generate the reflection data for them, and thus will not be garbage collected. Some of these macros are required for specific code features to work within the Unreal Engine and are modified and automated when created a class. Below are the basic macros. We will do a quick overview of what each is. UClass is used to tell Unreal to generate reflection data for a class. The class must derive from UObject for this to work. UStruct is used to tell Unreal to generate reflection data for a struct. UProperty is a macro for variables that is a member of a class or struct, and they can also be tracked by the garbage collector to keep track of how many references there are to a UObject. UFunction is used for functions of a class or struct. These markups also allow for specific features to be used inside of the parentheses. But if you don't want to use these features, want this garbage collected, you can add the macro and that's it. We will be quickly going over UFunction and UProperty as they are the most commonly used macros. UProperty is a macro that we would declare above a variable for it to be garbage collected, shown in Blueprint, used with networking, or also known as replication, or edit the value within the editor, which is also known as serialization. To specify what we want shown in blueprints or in the editor, we would have to fill in specific keywords within the UProperty's parameters. Common keywords are blueprint read only, blueprint read write, edit anywhere, visible anywhere, and many more. As we go through the course, we will be using some of these keywords to show how they work along with explanations of what they do. To access the complete list of view property specifiers, they can be found in the Unreal Engine documentation page, which is openly available in the links below, along with a wiki page for all of these specifiers. UFunction is a macro that we would declare above a function for it to be called within Blueprint or used with replication. The UFunction macro works the same way as it does with UProperty, where you place it above a declared function and fill in the parameters with specific keywords for it to work. Common keywords are Blueprint callable, Blueprint pure, Blueprint native event, and many more. As we go through this course, we will be using some of these keywords to show how they work, along with explanations of what they do. To access the complete list of UFunction specifiers, they can be found in the Unreal Engine documentation page, which is openly available in the links below, along with a documentation page for all of these specifiers. Unreal features some basic gameplay classes that are built off of Actor that became default classes that must be used for the game to function at all. First would be the player, and the player is a player controller class, which takes input, allows for HUDs, and camera management, while an AI controller can be used the same thing as player controller, except it's for AI or non-player controlled pawns. Both of these classes are subclasses of the controller class, which comes from the actor class. Controllers are actors that are responsible for directing a pawn class via a phrase called possess, which takes control of the pawn. A pawn is an actor that can be possessed by a controller, and this includes any subclasses of controller, such as pawn or player controller, or AI controller. Pawns are normally what you would visually control within the level, such as soldiers, heroes, and so on. A character class is a subclass of pawn, so it would have all the features of pawn while allowing us to use pre-built code that can allow us to have the ability to move around in the world, including in a multiplayer environment, and this is a good class to start from and to build off of. Finally, we have the game mode class. This is an actor that is automatically created with each level. Each actor in the world should have access to the game mode for that level, being a sort of global actor within the world. The game mode keeps track of the player controllers within the world, as well as automates spawning features for each player controller. One of these spawning features is that the player controller starts with a predefined pawn, because the player controllers are required to have something to control. This can all be set within the game mode. There is a process of the game engine starting and then launching the game. This is called the game flow. There are two main paths for this, editor path and standalone path. The general order of events is to initialize the engine, create and initialize a game instance, and then load the level, which creates the game mode, and finally start playing. However, there are some differences between standalone and editor modes, both in terms of the exact order of some of the functions that are called, and they eventually do converge at the start of the game. The flowchart shows the editor startup on the left side and standalone on the right, with editor having to do extra steps by starting an engine version of the game for debugging and then catch up to standalone by initializing normally. To examine the image in more detail, you may go to the link provided, which can also be found in the Unreal Engine documentation, which is freely available under the Game Flow Overview tab. In the next video, we will be creating our project in Unreal Engine 4 and its initial setup. Welcome to Section 2, Video 4, creating our Unreal project and its initial setup. In this video, we're going to create our Unreal Engine 4 project and set up said project. First, we must install Unreal VS, which is a free plugin that comes with the Unreal Engine for Visual Studio 2015. Open the File Explorer, find where your Unreal Engine is installed, go to Engine, Extras, Unreal VS, VS 2015, which is the version of Visual Studio that we are using, and run the Unreal VS extension installer. Select Install. Now we can close the installer and close the File Explorer. Open the Unreal Engine launcher and select Launch for 4.17.2. In the Unreal Project browser, we have two options for new projects. Under the New Project tab, we have Blueprint and C++. We will be using the C++ project. They have many templates for Visual Studio and Unreal Engine to use within C++ and Blueprint. We will be using the Basic Code project, which is just an empty project. Select where you want your project to be at within your computer and name it CPP_packed. We will start with starter content, which are assets that are provided by the Unreal Engine for free. And depending on your computer, we can start with maximum quality or scalable 3D, which is low end. And we'll be using desktop/console for our target hardware. Select Create Project. Now that the Unreal Engine is open, we will be changing the layout to better fit our screen and adding some other UI elements for it. First, go to Window, go to Developer Tools, and select Meshes Log. Click and drag down next to the content browser so we can easily switch between them by selecting it. Next, select the Hide or Show the Sources panel, which will show a tree of all the content that is in this project, as well as show us C++ classes that we can use. Next, click and drag the Modes panel next to the World Outliner. Organize your spacing by clicking on these white bars next to it or below it to space it out some more. Select Window, go to Developer Tools, and then select Output Log. Click and drag Output Log to snap it to the right of Content Browser and Message Log. Right-click on Output Log and select Clear Log to clear all the text within your log. Adjust your project accordingly for sizing. Select World Outliner to show our outliner, which are all the objects or actors that are within the level. Next, we will create an empty level. Go to File, New Level, and select Default. Select Save Current, and we will save it in our Content folder under the name map_gameplay. Select Save. Select Save All, just in case. Right-click on our output log and clear the log, so it's nice and empty. And now we will create a C++ class, so that way we can delete another class that comes with default projects. Select C++ classes, open CPP Packed Tutorial folder, and you will see there is already a class here. We will be deleting this soon, but to do so without messing up our project, we will have to create another class. We can also create our folder structure by doing this, by right-click and create New C++ class. You can only do this within the C++ classes folders. If you are not able to access this for some reason, you can select File and New C++ class. We will create a new class, and it will be of type Character. Select Next. We will name our class Base Character. Select Public, and this will add a path folder to our path, which is public. We will add another called Characters. Select Create Class, and this will compile the code and then send it to Visual Studio. Open Visual Studio. You may see tons of errors and squiggly lines. This is just IntelliSense within Visual Studio not working correctly with the Unreal Engine's source code. First, go to where our toolbars are and right-click and select Unreal VS. This will add extra options that come with the Unreal VS plugin. Next, let's close the base character CPP, which is called our source file, and the base character.h, which is our header file. We will open source and open our cpp_packtut.targetcs, not the editor version. To save time for these videos, I will be copy and pasting all the code and then explaining all of it. So what we changed was the modules that the IntelliSense will load and have them already added within the project. This is honestly a quality of life reason, as well as allowing us to access all of our code without having to add in extra folder directories. Next, we will open the cpp_pack tutorial folder, and then we will open the .build file. Next, we will add the modules for UMG or UI for Unreal Engine. These are also adding libraries to our code that we can use, such as UMG and Slate Core, which allows us to use UI within C++. We can close both of these files now. Go to Build, Rebuild Solution, and this will rebuild the solution and projects within C++ for this Unreal Engine 4 project. Alternatively, you can go to the Unreal Engine editor and select Compile. It also lets you know if a hot reload was completed when you started from Visual Studio. Next, let's work on deleting this game mode. Close Visual Studio and right-click on this game mode base C++ class and select Show in Explorer. Now that we have this location open, we can close the Unreal Engine. We must delete the source and header files of this game mode class by selecting them and then deleting them. And then we can go to our project file, right-click on the uProject file, and select Generate Visual Studio Project Files. Next, we can open the Visual Studio solution, or project. Now that Visual Studio is open, select Build and Rebuild Solution. To know whether or not your solution finished and successfully built, it will say Rebuild All and whether or not it succeeded, failed, or skipped. It should be 2 because that is the project and then the Unreal Engine. So the Unreal Engine succeeded and then the project succeeded, thus being 2. Now we can open our Unreal Engine project. Go back to the File Explorer that we had open and double-click on uProject. Now that Unreal Engine is open, we must change the Open Project map that starts up when the engine is opened. Select Edit and Editor Preferences, and first we will turn off autosaving. You can turn this on by going back to the Editor Preferences and selecting Loading and Saving, and select Enable Autosave and have it with a check mark. We can close this, and then go to Edit, Project Settings, Maps and Modes, and change our Editor Startup Map to be Map Gameplay. Close the Project Settings tab, and open our Map Gameplay file by double-clicking on it. Next, we will change the floor. Select the floor asset within the world, or you can select it within the viewport and delete. Next, go to Modes, Basic, and add a cube, static mesh actor. In our transforms for this actor, we have location, rotation, and scale. To set our location to 0, 0, 0, we just simply select Reset to Default. Go back to World Outliner, and let's rescale the cube to be 50 by 50 by 0.1. Next, we will change the material to whatever we want, since this will be our ground. Scroll down to Materials. In Element 0, we can select a new material in the drop-down. You may choose whatever you want. To pan the camera and move around, right-click in the viewport and move your mouse. This allows you to look around within the world. To move in the world, you would use right-click and hold and WASD to move around. To move up and down, still holding the right-click, E and Q to go up and down. Let's rename our cube to something better named and aptly suited. Select the cube and select F2, and let's change this to floor. To orbit around an object, hold the Alt key and left-click, and then move the mouse. To deselect an object that you have selected within the world, hit the Escape key. Now that we've saved everything within our C++ classes and everything, now that we've modified the floor, let's save all these changes. Select Save All, and select Save Selected. In the next video, we will be exploring the Unreal Engine interface and importing our assets. Welcome to Section 2, Video 5, exploring the Unreal Engine 4 interface and importing our assets. In this video, we are going to familiarize ourselves with the Unreal Engine 4 interface, build out our gameplay level, and import our assets. The Unreal Engine 4 interface is a completely customizable interface that allows you to modify the layout of panels, or windows. The content browser, which we have placed in the bottom left corner of the screen, is a file browser for assets or files that are related to the project. To modify the layout of panels, we can simply click on the tab of the panel that we would like to move and drag that panel to a new location. As you may see, the engine features a panel snapping feature that allows us to snap panels without having to resize them. The panel that features our game world is called the viewport. This is our view into the game world without having to control the player. Let's go over some of the viewport features. In the top left corner of the screen is the arrow of the viewport for options of the viewport, such as field of view, debugging any performance problems from our art assets, and other such options. Next to that is our Perspective tab, which we can change to snap our viewport to a new view. Next is our Rendering mode. This will default to lit mode, which is how the game will look when playing. Next is our Editor Flags tab, which we will use to show or hide specific developer features that can only be seen in the viewport and are meant to help with development. Now we will move over to the top right corner of the viewport. Let's start with our multi-viewport, which allows us to use multiple viewports to open and maximize a specific one that we would need. Next is our camera speed within the viewport, which controls how fast our camera moves within the world in the viewport. This will default to 4. Next is our scaling snapping, which we select the drop-down to change the snapping amount, or to turn off the snapping we can select the icon next to the drop-down. Next is the rotation snapping, which works in concept the same as scaling snapping does, but with degrees. Next is translation snapping, which works the same as rotation and scaling snapping, but with moving an object within the world through the viewport. Next to the translation snapping toggle button are extra options for translation. Next is the toggle button between transform gizmo within the world and local space. Finally is the translation, rotation, and scaling gizmo buttons, which allow you to switch between the three via the button that is selected. You may also press W for translation, E for rotation, and R for scaling. These buttons on the keyboard are known as hotkeys. The Details panel shows all of the available options that can modify an object within the editor. In other game engines, this may be known as the inspector. At the top of the screen is the toolbar, which features the large buttons such as Save, Source Control, Content, Marketplace, Settings, and many more. At the bottom of the screen is the output log, which is a console that would tell us exactly what the engine is doing in some manner. To deselect an object within the viewport, you can select the Escape key. Next to the content browser is the message log, which will notify us of any errors or warnings within our code or that occurred during gameplay or runtime. Now we will start by building our gameplay level. Select the Modes panel and select Basic, had it already selected it already. If the Modes panel is not showing up and you are missing a panel, you may select Window in the top left and check Modes if it is not showing up, or whatever panels you may require. This is where all the windows for Unreal are that can be used right now in case you close a window that you didn't intend to close. Scroll down in the Modes Basic panel and click and drag any of the basic shapes to use for the level, such as cubes, spheres, cylinders, cones, etc. We are currently using a plane for the floor, and the plane cannot be seen from below. While holding the right mouse button, press any of the W, A, S, and D keys to move forwards, backwards, left, or right, and this also works with the arrow keys. Hold the right mouse button to click and drag in the viewport to look around. While holding the right mouse button down, press E or Q to move up and down within the viewport. These are commonly known as first-person controls. You can also hold the Alt key and left-click and drag to orbit around an object that you have selected or within that general area of where you selected. If you would like for an object to snap to the ground, you can do this by selecting the object and pressing the End key on the keyboard. Another option may be to select the object, right-click, transform, snap and align, and snap to floor. You may also drag in assets from the Starter Content folder into the viewport, which works the same way when dragging in from the Modes panel. You may pause the video now to build out your level, while also not being overly complicated. Once you have finished making your level, we will be adding some extra post-process effects, such as a light mass importance volume, which will build out our lighting for our level. Once you have finished making your level how you would like, go to the Modes panel, go to Volumes, and scroll down until you see Light Mass Importance Volume, and drag that into the level. We will then scale this in the X, Y, and Z by 10,000. We will build our lighting for our level, and this volume will let the engine know that we only want to build lighting within this volume. Go to Build and select the Build Options drop-down arrow in the top toolbar, and select Build Lighting Only. Once lighting has finished building, we will select the Save All option in the content browser and This will save all of our assets and changes that we've done within the level, as well as building our lighting. Select Save Selected, and this will save all the work that you've done. We will now import our provided assets into Unreal. Now, close the Unreal Editor and Visual Studio if applicable, and then open the File Explorer, go to the location of the assets provided, and copy those files. Now we will go to the Project folder location and open the Content folder and paste the provided assets within the Content folder. It is important to paste it into the Content folder, as Unreal's file management system will only pick it up when it is imported directly to that folder. In the event that you pasted it into the wrong folder, simply delete those files, open the project, save all, close the project, and paste the files into the Content folder. Now open the project to find all of those assets located inside. In the Content browser, select Filters, go to Other Filters at the bottom, and check Show Redirectors. These allow you to see any ghost file paths that were not cleaned up by the file management system. If any are found, you can right-click the Content folder inside the Content browser and select Fix Up Redirectors. This will take care of any ghost files. In the next section, we will be creating our player character. Welcome to Section 3, Creating the Player Character. Creating the Player Character's Code, Part 1, Basic Character Setup. In this video, we are going to set up our player inputs, set up our player health, and our sprinting state. First, let's go to the top left, under Edit, select Project Settings. Under the Engine category, go to Input, and we will be adding in some action and axis mappings. Let's start with action mappings by selecting the plus symbol to add one. An action mapping is code that will fire off when a key is pressed or released for this action. We will have 5 action mappings. The first one will be named Jump, the second one will be named Fire, the third one will be named Sprint, the fourth one will be named Pause Game, and the last one will be named Interact. For Jump, we will be adding the spacebar key. For Fire, we will be using the left mouse button. For Sprint, we will be using the left Shift key. For Pause Game, we will have 2 key inputs, so we can add another for that action by selecting the plus symbol next to the action. We will be using the Escape key and the Backspace key. For Interact, we will be using the E key. Now we will start adding some axis mappings. This works the same way as the action mappings, except it is constantly being fired and provides a float value, which will represent that value when it is pressed and 0 when it is not pressed. We will have 4 axis mappings. The first one will be named Move Forward, the second one will be named Move Right, the third one will be named Look Up, and the last one will be named Turn. Any inputs using the binding method are case sensitive. For Move Forward, we will have 4 key values. For the last 2, we will have them as -1 values when they are pressed instead of +1. This is to let us know to do the opposite of what this button is supposed to be pressing. So in the case of Move Forward with the W key or the up arrow key, which will be our 2 inputs for +1, our reverse of that will be the backwards movement, which is down arrow and the S key. For Move Right, we will also be using 4 inputs. And just like the Move Forward axis mapping, we will have 2 that are -1. For Move Right, we will be using the D key and the right arrow for +1. For negative values, we will be using the A key and the left arrow. For Look Up, we will be using the mouse input, which will be mouse Y. And for Turn, we will be using mouse X. Now let's close Project Settings and navigate to our base character inside of our C++ classes folders. Open it by double-clicking on base character. This will be our base class to build off of when we need a general kind of code to fire, such as damaging any players or NPCs nearby and such. The virtual keyword under begin plays function allows us to inherit this function down to subclasses so that they can use their own version of this function, and the override keyword so this function cannot continue to be inherited anymore past this class, blocking any subclasses from inheriting it, but it becomes cancelled out by the virtual keyword, which takes priority. It's good practice to have the override keyword on a virtual function if it's being inherited down, which helps the programmer notify themselves that this is a virtual function. We specify whether or not something is public, private, or protected if it has the keyword with the colon after it, and then any functions or variables below that are within that category of public, private, or protected. In the case of base character, we will not be using the setup player input component or tick functions, so we will be removing these. Be sure to save any work that you've done within the Visual Studio Editor by going to the top left where it says Save All, or save base character.h, which is just the file that you're currently in. Now let's go into our source file, which is the .cpp file, and clean up our other functions such as the setup player input components definition and the tick functions definition. Let's save our changes and jump back into our base character. Here we have added two functions, onDeath underscore implementation, and we've added three variables, two floats, which are the current health and max health variables, and a boolean, which is our state of whether or not we are sprinting for this character. The function onDeath has the uFunction macro above it to signal that we want specific features to be within Blueprint. In this case, we have added the Blueprint native event, which allows us to use this as a sort of virtual function that works within Blueprint. Because it is Blueprint native event, we must repeat this function, but with the virtual keyword and implementation after the function name. This will be our C++ version of the code within this function, while the onDeath will not have a definition, but that will be our Blueprint version of the code. The keyword pureVirtual allows this virtual function to not have a definition when it is declared. It is also important to note the comma afterwards. We must define it in any subclasses, or else the compiler will not accept it though. The keyword Blueprint callable allows us to actually call this function in Blueprint if need be, and the keyword category is required so that this function is organized somewhere within the Blueprint code library. In the case of current health, we will not be needing to use it within Blueprint, so we don't add a uProperty macro above it. For max health, we will be editing it within Blueprint and within our editor default values panel of the Blueprint. The edit defaults only allows us to edit this value in the editor, but only in the defaults menu of said Blueprint, but not on any instances that have spawned. The Blueprint read-write allows us to use this variable within Blueprint code for both getting and setting the value. For our sprinting boolean, we have a visible anywhere keyword, which allows us to see the variable within the editor, both in the defaults menu and on instances, but we cannot edit the value within the editor. Blueprint read only allows us to get this variable but not set it within Blueprint, while also being able to set the value within C++. This is typically used to allow a certain amount of control over some values that we wouldn't want edited by another teammate or team member that works only in Blueprint. Under the public category, we have our constructor, which is the same name as our class, except with a parameters above it, so that this code will fire when the object is created. Then we created three more functions as getters and setters for our variables. Since they are protected, we cannot access them publicly from any other classes. So we have these sort of functions to be able to access them in some capacity. For our get current health and get max health, we have the keyword Blueprint pure. This allows this function to be used for both complex calculations and for getting accurate values such as for floats. But you cannot change values within the function because of the way it is designed that for more advanced programmers that we won't be getting into. In the set current health, we have a parameter which is a type float value named new health, and we are setting our current health to equal new health. Let's jump into our source file and add some code to our constructor. Here we've gone into our constructor's function, which is a function that gets fired when the object is created in memory, and this is typically where you put your base default values and where you would create your components and such when the object is created. Here we have a simple if statement. The keyword if starts the statement, and using the parentheses asks whether or not this is true or false. If this statement is true, then we would enter the curly braces and execute the code within the braces. If it is false, then we would skip over the curly braces and continue on. Here we are checking if our current health is not equal to our max health. If it isn't, then update our current health to be equal to our max health. Now that we've done all of our changes, let's compile our code. Go to Build and rebuild the name of our project. This may change for other projects. In the output log, you'll see whether or not the code is compiling when it results within a succeeded, failed, or skipped line. In our case, the build succeeded where nothing failed and nothing was skipped. So we can jump back into Unreal Engine and see our code has been edited by right-clicking on base character and creating a blueprint class base character. But we can also create a C++ class derived from this, and we will create one now. We will name this player character. In our player character, you may notice there really isn't any code. This is because it inherits from base character, and thus inherits any functions or constructor values that have been set within it. We will set up our constructor for this class by copying and pasting the name of the class and then adding parentheses to it. One thing to note is that you must have the constructor within the public category. This is very important when creating an object within code. You must always have access to the constructor in case you wanted to add some extra variables or values to it when it is constructed. The reason why we have to specify that it is public is because by default everything is private. Let's add a definition for our constructor by copying and pasting the code within to the source file. Copy and paste the name of the constructor function, go to our source file, paste it, and add 2 colons, and then paste it again, and then add parentheses, and 2 curly braces. Now we have created our constructor, and defined it. And in the next video, we will be creating the player character's code, part 2, setting up our player character. Welcome to section 3, video 2, creating the player character's code, part 2, set up player character. In this video, we are going to create our player character's components and set up our ammo. Under the generated body, we have added in 4 pointer variables, each with their own specific class type variable that we are using. And we are using the keyword class as a sort of forward declaration for that class, meaning we won't have to include any header files of that class, just we have the general idea that this exists somewhere. The keyword blueprint read only means that we can only get this value, but we cannot set it within blueprint code. Visible defaults only means that we can only see this value within the class defaults of the blueprint, but we cannot edit it. We have added a meta tag, meaning we can use extra features of view property, and these features allow for light scripting of the editor for that value. The meta tag allow private access means that since this variable is private, we want to be able to access it within blueprint anyway by setting it to true. After our constructor, we will create our protected category. Here we are inheriting the begin play and on death functions from our base class, while the setup player input component function is being inherited from our pawn class. Then we are creating our ammo variables and a function that will check if we have ammo or not. The edit anywhere keyword means that we can edit this value in the editor on both instances and in the class defaults of blueprints. Here we are creating functions to modify the ammo values that can be called from another class. These are general getters and setters for our ammo, the same way it would work for getting and setting our health. Let's go to our source file, and in our constructor, we are going to start creating our components. The reason why we are having errors is because we haven't included those libraries. While in the header file, we have given the general idea that this component exists, we haven't actually given it a definition of what it actually is supposed to be, what it's supposed to do, those kind of things. And the way we do that in the source file is by going to the top under the header file for this class. In our case, it would be player character.h. Under that, and it's very important to put it under, we would include those components' libraries. In this case, the location of where those header files are. For the SpringArm component, it's located under the game framework / SpringArm component, and so on. These are our libraries that we would need to be able to access each component's code. And in the case of the skeletal mesh component, we would need the library for skeletal mesh components. And here we are creating our components and saving their locations in memory so that we can access them later, using our pointer variables that we created at the top of our player character header file. It is very important that you must always set up attachment for those components, or else the engine will crash, as components are required to have a parent. We are then setting some default values for our components. In the case of SpringArm, we are setting our relative location, a target arm length, which is how long the camera's spring arm is, turning off collision test, setting our pawn rotation to be true, meaning it will use the control rotation, not a separate one that we would have to set for the spring arm separately, and setting what we can and cannot inherit from that pawn rotation. The f vector is actually just a struct for x, y, and z values using floats for each x, y, and z value. For our camera, we are setting its field of view to a regular value of 90. After we create our components, we are then setting the default values for our variables. You may notice that we are using max health and current health again. This is because it is protected and allows us to change the current value of this subclass. Back in our header file, let's add definitions for our begin play, setup player input component, and on death implementation. Instead of having to do the long way, which is copy the name of the variable or function and pasting it back into our source file and repeating a very tedious task, we can actually select it with the cursor or press Ctrl+, which will show our options or additional actions that we can use, and select create definition of this function inside of our source file. And it will automatically set that up for us. And we can close this and repeat that process for each one. Once you finish that, we will go back into our source file. Select Save All to save those changes. And let's start it on our begin play function. Here we are doing what we did with our health in the base class, but for our ammo, and we are calling super begin play, meaning since it is virtual, this allows us to call each iteration of begin play up the chain at once, as it is generally good practice to call super and then the name of that same function inside of that function. Thus it will go up the chain to its parent, and up the chain to its parent, and up the chain to its parent version of that same function, and so on and so on. In our setup player input components, we are doing the same thing by calling the super version of this function and then adding a specific special kind of if statement called check. And what this is a macro that will cause the program to crash if it is false. And this is a sort of very strong if statement where we need this to be true and only true. For on-death implementation, we don't need anything currently, so we will leave that empty. Back in Unreal Engine, let's select Compile to compile that code. While this is compiling, let's add a folder in the Content folder for blueprints. Go to Content, right-click, and select New Folder. As you can see, our compile finished, and enter Blueprints. This is where we will save all of our subclasses from our C++ to Blueprint classes. Let's go back to our C++ class, right-click on Player Character, and select Create Blueprint Class based on Player Character. Let's place it in Blueprints folder and name it Player Character _BP. This is the blueprint editor. At the top is our compile button that has to be pressed for the game to run, and we would have to press this every time we make any changes to any values within this blueprint, whether it be blueprint code or any base values in our class defaults, where we can find all of our values that are editable within the editor. Here we have our components that we created within C++, and they have been automatically added and set to their locations. The viewport works the same way as it does within the level viewport. Construction script is a special blueprint graph that fires off from construction script's beginning node that cannot be deleted, and happens after the object has been created or spawned, and then runs the C++ code and then runs the construction code afterwards, because C++ always gets priority in those cases. To move around within the graph, right-click and drag. To add any nodes, just simply right-click, and left-click anywhere else to get rid of that. The event graph is the same way, but for any other general functions or events that need to be fired. Construction script is specifically for construction script code that is meant to be fired when this object gets created. An event graph is for anything else. In the next video, we will be creating the player character's code, part 3, basic movement. Welcome to section 3, video 3, creating the player character's code, part 3, basic movement. In this video, we are going to set up our inputs to connect to our player and set up our visual aspects of movement. First, we are going to set up our visual asset by going to the content browser under first person, animations, and open our first person anim BP. This is an animation blueprint that allows us to code specific animations based on our code's values. Drag out of try get pawn over and enter in cast to player character BP. Connect the execution pin on the left to is moving execution pin on the right, and connect the execution pin on the right, not from cast failed, to sprint check execution pin. Out of this, we're going to get our variable for get is sprinting. Connect those two for is sprinting and sprint check, and we now have set up our animation blueprint to connect to our player character's movement. Select save and then compile. Let's jump into our player character blueprint and add that visual asset to it by going to FP mesh. Under the skeletal mesh, select SK mannequin arms, and for our anim class, we will be using the first person anim BP. As you can tell, it is offset greatly, so we're going to fix that by going to location in the Z and change it to -160. For our rotation, we will be setting the X value to 5 and our Z to -15. Select save and then compile, and we have set up our asset. Let's open our C++ class for our player character. Under the public category, we are going to add in 3 float values or variables. These are going to be setting up our player's camera movement rate and setting up our sprint speed variable for future use. Here we are creating our functions for moving left and right using the axis values that we created previously as our scalar value. This applies for lookup and turn at rate, but for our camera instead of using actual movement. Here we are setting up our camera's min, max, pitch values. We won't be needing this for our movement speed because the camera is not controlled by the character movement component, which will handle that for us. Here we are setting up our previous walk speed variable for future use under the private category because we won't be needing it outside of this C++ class. Let's jump into our source file, and in the constructor, we are going to set up our default values for our camera movement and our camera's pitch, min, and max values, as well as the default sprint speed. Let's go back to our header file and create our definitions for our move forward, move right, look up at rate, and turn at rate. Now that we've done this, let's go into our source file and add some definitions to that code. Select Save All, and in the turn at rate function, we will add in a already created function that is created within all pawns, and what we are doing is affecting our control rotation's yaw rotation by adding some math, which what we are doing is incrementing very slowly in the yaw direction every frame by using the world's delta seconds by the amount that we would like, which is our base turn rate. Our rate is actually our scalar value from our axis value that will be either -1, 0, or 1. In the lookup at rate, we've added a more complicated version of what we were doing in the turn at rate. Here we are checking to see if our spring arm component reference is valid by putting it within a if statement, and then we are checking the initial rotation and saving that for our frame. This is all happening within one single frame. Then we are saving the clamped pitch of that saved rotation if we were to rotate it normally. Then we are setting our rotation that we saved for its pitch to be the clamped version. And then we are applying our new clamped rotation to our spring arm. We do this so we can independently rotate the pitch of the spring arm while constraining it to our min and max values. You may notice some variables within this function. These are temporary variables that get deleted after it ends at the end of the function with the curly braces. We are also using the keyword const for constant so that the compiler will load this faster in the computer's memory, and it is faster that we didn't use this. We are also using the keyword constant so that the compiler will load this faster in the computer's memory, and if it is faster, then we won't be using const otherwise. We are using the keyword const so that the compiler will load this faster in the computer's memory, and it is faster than if we didn't use const. But we can only use const when we don't plan on changing that value anymore or anywhere else in this function. In the moveRight function, we are telling our character component to move us in the direction that we would want at the rate that we would want. In the case of our direction, it is the right direction of this actor, and in the case of our rate, we are using our scalar value. We are also checking if our button is being pressed by checking if our scalar does not equal 0. If it does, then we aren't moving and there's no point in continuing. Here we are doing the same thing as we did with the function moveRight, except with the forward vector instead of the right vector. In our setup player input component, after the check function or macro, here we are binding our axis values as well as binding our action for jump to an already created function within the character class for jumping. For binding an action or axis, we require the name of the binding, and it is case sensitive. For the actions, we need to specify whether or not it is being pressed or released. And then for both, we also need to supply an object, which in this case it is this class and this object, to bind it to, and then the function within the object to bind it to. It doesn't matter whether or not it inherits through it, as long as it is somewhere within the inheritance of this object. These functions are bound when the engine is initialized and happens only once. Now let's go into our engine and compile. Now that our engine has finished compiling, let's go to Blueprints and drag our player character BP into the level and scroll down in the Details panel to the very bottom, and under Auto Possess Player in the Pawn category, let's change Disable to Player 0. Then select Play, and as we move our mouse around, we can look around. As you can see, our thumb in our hand are casting a shadow, as well as our arms. And if we press W, we move forward, A moves left, and D moves right, because A is a negative value of D, so it'll just move in the opposite direction, and this works the same with the S key. This also works with the arrow keys. And if we press the space bar, we jump. Hit the escape key to stop playing. In the next video, we will be creating the player characters code part 4, sprinting. Welcome to section 3, video 4, creating the player characters code part 4, sprinting. In this video, we are going to set up our sprinting, attach a gun to our arms for visual clarity, and prepare our shooting functionality. First, we are going to add our gun to our player. Let's open up our player character blueprint. It will automatically show up as a data-only blueprint in some cases. To get everything within the blueprint editor, simply select Open Full Blueprint Editor in the top of the class defaults. Select Gun Mesh. In the Details panel under Skeletal Mesh, select SKFP Gun. Select Save and Compile, and we can close Player Character BP. Let's open up our player character C++ class. Under Protected, we're going to add a few functions and variables. Here we are declaring our sprint start and sprint end functions that we will be using both in C++ and Blueprint in the future. We are also declaring 2 pointer variables for particles that we will spawn when we shoot our gun. Under Private, we're going to add a function that we don't want to show up in Blueprint, so we're just going to leave it alone without a U function. We're declaring the private function for spawning particles while also having a vector for our parameter, which will be particle location. Let's add our definitions to our functions. For sprint start and sprint end, only create the definition for the underscore implementation. Select Save All. Let's add the code to our source file. In our constructor, we are setting the default values for our pointer variables by setting them to null, which for pointers is the keyword nullPTR. This is also short for null pointer. In begin play, we will be attaching our gun to our arms or FP mesh. Here we are attaching the gun mesh to the component which is our arms mesh and snapping it to a socket which we have named grip point, which is already established on the skeletal mesh. If the skeletal mesh does not have that socket, then it will just return an error and not attach it to that mesh. In our on-sprint implementation, we are setting our sprinting boolean to true and turning off the ability to shoot by setting our shoot boolean to false. Then we are saving our walk speed for when we are not sprinting and then setting our speed to our sprinting speed. You may notice that we are getting errors. This is because we haven't included the library for a U character movement component. Scroll to the top of the page and let's include that file. Now we don't have any errors. In our on-sprint end implementation, we are just setting the opposite of what we did for sprint start, where we would set the sprinting boolean to false, and then we are setting our walk speed to the previous walk speed, and finally allowing us to shoot by setting can shoot boolean to true. For the beginning of the spawn shooting particles function, we are checking to see if our particle pointer variables are valid by putting them within an if statement, which will automatically do the same as typing in not equals null pointer, which is a null value. Then we are spawning our particles and saving that spawned particle as a component pointer. So we are getting the location in memory of where that particle has been spawned and reusing it again to be able to affect its world scale in 3D by inputting a vector and inputting a float which will automatically set it for its x, y, and z. Then we are setting a vector parameter that is specific for this specific particle, which is our trail effect, and we are setting it where the end location of the particle will be at where our particle location is. We don't need to set the beginning part because this will start from where it is spawned, which we have set to be our socket location on the gun, which is a muzzle. For hit effect, we are doing something similar, but we are only just setting the scale to 0.25. You may have noticed the errors for our temporary variables, and this is because we haven't included those libraries, as well as for a U gameplay statics, which is a library of functions that we can use to make our quality of life easier and better in terms of coding. Scroll to the top of the page, and let's include those libraries. Now let's bind our action by going to Setup Player Input Component. Here we are doing the similar thing of binding an action like we did with jump, but we are doing it for sprint. Since this function is a Blueprint native event function, we only need to call the original function name, and it will automatically call both the C++ and Blueprint versions of the code. Must never call the implementation version of the code. It is generally just good practice as well. Let us compile and test by going to Build and rebuild our project. Now that our project has finished compiling, let's jump back to Unreal Editor and let's open our blueprint for player character BP. And in our class defaults in the details panel, go to gun under the category gun and let's set our trail and hit effects. For our trail effect, we will be using the P assault rifle trail particle system, and for our hit effect, we will be using P explosion. Save and compile. In the next video, we will be creating the player character's code part 5, shooting. Welcome to section 3, video 5, creating the player character's code part 5, shooting. In this video, we are going to set up our shooting functionality and prepare our HUD classes. First, we are going to create two C++ classes while creating another folder for organization, which will be for UI. In the C++ classes folder, under the public folder, right-click and select New C++ Class, scroll down, select HUD as our base class, select Next, and we will name this class Generic HUD. In our path, we will be adding in /UI. This will create a new folder category in the public folder, which will be for our UI. Select Create Class, and the engine will compile the code and create our new folder. Now let's create our other class. In our UI folder, right-click and select New C++ Class, select Show All Classes in the top right, and enter User Widget. We will be using the user widget as this base class. Select Next, and let's name it Widget Gameplay. Select Create Class, and let the engine compile and create this new class for us. Now let's close our Widget Gameplay and Generic HUD classes, and in our player characters header file, under the protected category, we're going to add in some code. Here we are creating our inherited function that is on all actors called takeDamage, which returns a float value for the amount of damage applied. This will be where our player can take damage. Then we are declaring our onFire function, which will handle all the functionality of firing our gun. And then we declared our variable pointer for an animation asset to play when firing our gun. And then we declared the damage amount of the gun when fired. Let's create our definitions of our takeDamage and onFire implementation, but not the regular onFire functions. Now that you've done so, go into our source file, and at the top in our libraries, we'll be adding in the animation library for our animation asset to play correctly. In our constructor, we are setting the default values for our takeDamage amount and setting our animation variable to null, which is null PTR, or null pointer. Our damage amount will have a default value of 10. Here we are first calling up the chain for our takeDamage, which is our super function, and then checking if our current health is less than or equal to 0, which if it is, then return 0 as the amount of health we have, since that means we are pretty much dead. Then we are checking by subtracting our health and saving it to use later, which we will use to check if it is nearly equal to 0, or using this symbol if it is less than 0, meaning we are dead when it is subtracted, and we are locking our current health to 0 and then calling the onDeath function. If we aren't going to die when we subtract our health, then we just update our current health to the subtracted amount, and then we return the subtracted amount, or 0 in this case. For our onFire implementation, let's start with the beginning of our shoot function by first checking to see if we can shoot. If we can't, then we return out of the function, meaning we don't continue on doing the rest of the code. We just immediately stop here, and that's it. Then we check if we have any ammo, meaning if we have unlimited ammo off, and we don't have ammo, that means we have 0 bullets entirely, and we should not be firing our gun. Then we place brackets so we can organize our code, and then declare a temporary vector variable we have set to a 0 vector, which is a shorthand term for setting it to 0 on the X, Y, and Z. Then we declare our fHitResult hit variable, or struct, which contains almost all the data about an invisible ray that gets fired, and this includes what it hit, what time it hit, the direction of the hit, and so on. Then we have declared two vector variables, one where the invisible ray should start at our camera's location in the world, and then a second is where the ray should end, which is the camera's location in the forward vector, or forward direction of the camera, and at a length of 10,000 units. So, whichever direction the camera is facing, 10,000 units forward is where the ray should end, which it will start at the camera and just shoot all the way to that point. Then we are declaring another struct variable, which will be the objects for the ray to ignore, which we have specified to be our player, with these two lines of code. Then we actually fire the ray within the world to hit anything that blocks the collision channel visibility. In Unreal Engine, invisible ray or raycast is known as a trace. or a shape trace, and in this case it is a line trace. Now that we have fired our ray, we check to see if we hit anything with the blocking hit boolean and the actor that we hit to see if it is valid. If not, then we set the end location of our particles to be at the end trace's location. If we did hit anything, then it's valid. Then we set the particle's end location to be where it hit, which is our impact point, and then we are declaring a general object that handles damaging actors called a uDamage type, and we are creating a generic version of that class, which we later use to specify what type of damage we are using. In this case, it is point damage. Then we are actually damaging the actor that we hit and importing the damage type and who damaged it. After our checks for anything hit or damaging it, we spawn our particles using the function that we created earlier and inputting the particle location, which we have set to be either the end of the trace or to where we hit, which is our impact point. Then we are checking if our fire animation pointer is valid, meaning we actually have something in there and it's not empty, and then getting the animation blueprint instance from our arms mesh and telling it to play the fire animation. And finally, we are checking if unlimited ammo is off. If it is, then we subtract one bullet from our current ammo, which is specified by the ---- after current ammo. Here we are binding our fire button input to the onFire function when pressed, which is in our setup player input component function. Now let's compile, save all, then go to build and rebuild project. Now that it finished rebuilding, let's open up our blueprints and our player character BP, open up the full blueprint editor, go to viewport, and on our class defaults, select under the gun category, we have the fire animation, which we will set to first person fire montage. Select save and compile, select play, and let's test this. Here we have our gun attached to our arms, and as we move around, it moves with us. When we shoot, it fires our gun. Hit escape to close the game. And in our ammo category, if we turn on unlimited ammo, select save, compile, select play, we can keep firing with no problem. In the next video, we will be creating the player's HUD, Part 1, basic setup for UMG widgets. Welcome to Section 3, Video 6, creating the player's HUD, Part 1, basic setup with UMG widgets. In this video, we are going to set up our HUD class and set up our widgets code. First, we are going to set up our HUD class. Let's go into our UI folder in our C++ classes and open up our generic HUD. Here we are declaring our constructor for this actor, and then we are creating our getter functions for our variables within the protected category. We declare 3 variables, which are class references that can only inherit from the user widget class, which is what we will be using to visibly edit and show off our UI. Back to our functions, we declared a function to show a specific menu, which inputs a subclass of user widget, and then we have to set our forward declarations in the parameters of user widget by including the keyword class. Then we are inputting a boolean to check if this is UI only mode of gameplay or if we are using game only gameplay, which means we only want to receive input from our player controller when this is true, and when it is false we don't want to receive any button presses at all. And our final boolean is being inputted in for if we want to show the mouse cursor on screen if it's true, and if it's false we just don't show it. We have this function returning a boolean because we want to know whether or not we succeeded with showing our UI element to the screen. Then we have another function which handles removing all UI elements from the screen. Let's add our definitions. For our constructor, we will have to copy and paste it and hand make it instead of automatically creating it using Visual Studio. And in our libraries, we will have to include the UI / since our path to our header file is not correct. Save all, and Visual Studio will compile these libraries back into our source file, thus removing our errors. Here we are setting our variables to null, but since they aren't pointers but they do require references to a class, we are going to use the generic C++ null value instead. In our function's showSpecificMenu, first we are checking to clear all UI elements from the screen, and then we are checking if class_to_show is valid. Then we create our widget and save that created widget as a temporary variable so that we can add it to the screen. We are then checking if GameOnly is true. If it is, then we set our player controller's input mode to GameOnly by inputting a construct by calling the constructor function for that struct. This is why we have constructors be in the public category, so that we can create one and also have the default values set automatically. If GameOnly is false, then we declare a struct for our input mode, being UI only. Also, when a struct is declared, even as a temporary variable, it will automatically call the constructor for that struct. Then we are telling the input mode to not lock the mouse within the viewport, so in case we need to click out of the screen or to another window, we can. Then we confirm and update our input mode for our player controller, and finally show our mouse cursor depending on what the inputted show mouse boolean is, and then we return true, meaning we leave the function and return true so that way we know we successfully created our UI. If we return false, that means the class we inputted was invalid, which would be the only reason to fail. Here we are calling an already established function from a function library to remove all widgets from the screen. We use this function in this class because we just include the generic HUD's class header file, then we can just access the other functions as well, including this one, and any getters or setters. Now that we've finished with our generic HUD class, we can actually open up our widget gameplay files by going into our Solution Explorer and double-clicking on widgetgameplay.h for the header file and widgetgameplay.cpp for our source file. Let's fix our path to the header file inside of the gameplay's source file by adding UI/. In our header file, we are creating a pure but not constant functions for getting the current health and ammo values from our player character under the protected category. This is so we can connect UI elements to these functions and it will automatically fire those functions constantly as a sort of binding. Let's add our definitions. Now in our source file, let's add some libraries. Here we are adding our libraries that we will be using within this source file, which will be our player and the text file for returning our ftext struct. Here we are getting access to our player class that owns this widget, and then saving that player class that we tried to get from our owning player pawn, which casting will check to see if we find any sort of code that involves the A player character in terms of inheritance of this pawn, and then we save it as a temporary variable and we put it within an if statement to see if it successfully did this or not. Another way you could have done this is by putting all of this in one line above it and then checking if player is valid in the next line. But this is cleaner and allows us to organize our code easily. Then we are getting the current and max health values and dividing them for a value between 0 and 1, and then clamping that value just in case so it can't be out of the range of 0 and the value of 1 as our min and max values. And then returning that value as our float value, but if the cast failed, then we would return 0.5 as a backup. Here in getCurrentAmmo, we are doing the same thing that we did with current health, but just using the flat getCurrentAmmo and using the ftext automated function where it uses as number, it converts the integer that is inputted and converts it to an ftext variable in which we can return that. In case the cast failed, we just return a value of 999 just to let us know that we did not successfully cast. Let's build, rebuild, and our project file. In the next video, we will be creating the player's HUD part 2, building the widget blueprint. Welcome to section 3. Video 7, Creating the Player's HUD Part 2, Building the Widget Blueprint. In this video we are going to build our widget blueprint and prepare our game mode class. Now let's build our widget blueprint. Go into the Blueprints folder of our Content folder, right click, create new folder. We'll name this Widgets, and inside the Widgets folder, right click, User Interface, Widget Blueprint, and we will name this Gameplay HUD WB. Let's open it up. This is the widget blueprint editor or designer. Right click and drag to move around within the viewport. Left mouse wheel to scroll in and out. On our left is our palette where we can add in different components or hierarchy parts of this UI, such as an image or a button, border, text, etc. First we will be adding in a canvas panel. We will name this Crosshairs. We will be adding in 5 images. Let's rename these to right crosshair, left crosshair, bottom crosshair, top crosshair, and center crosshair. Let's save and compile to save our work. The canvas panel for crosshair, select anchors, and let's set it to the center anchor. Let's set its position to 0, 0. Let's set its size X and size Y to 75, and its alignment on the X and Y to 0.5. For our center crosshair, let's set its position in the anchor to center, and its position to 0, 0. Its size on the X and Y to 2.5, and its alignment on the X and Y to 0.5. For a top crosshair, let's set its anchor to the top. Its position will be 0, 0. Its X and Y will be 2.5 for the size. The size and the Y will be 25. And the alignment on the X and Y will be 0.5 and 0. For the bottom crosshair, we will set its alignment to the bottom on the anchor. Its position will be 0, 0. Its X will be 2.5, and its size in the Y will be 25. Its alignment will be 0.5 and 1.0. For left crosshair, its anchor will be in the left, 0, 0 for the position X and Y. For size X it will be 25, and size Y will be 2.5. Its alignment will be 0 and 0.5. For the right crosshair, its anchor will be on the right, 0, 0 on the position on the X and Y. For size X we will put it to 25, and Y will be 2.5. Its alignment will be 1 and 0.5. Select Save and Compile. And now let's add another border to our canvas panel. Then we will add in a vertical box and a progress bar to that vertical box, and text to the vertical box as well. For our border, its anchor will be in the top right. Its position will be in the X, negative 650. And its Y will be in the 100. Its size will be 500 in the X, and its Y will be 150. For the progress bar, select Fill, and its bar fill type will be right to left. And we will change its color for fill and opacity to green. To see what the color is, you can change the percentage. This will be the default value, which we will set to 0.5. For our text block, we will align it to the right on the horizontal alignment. We will change the text to ammo, and we will change the name of the text to ammo text. And we will change its font size to 35 by going into the font and size. Let's also change our border for its brush color to be black, and let's change its alpha to 0.25. Save and compile. Now we are going to reparent this widget blueprint to the C++ version we made by going into the graph and then setting in the class settings the parent class to widget gameplay. Save, compile. Let's go back to the designer, select ammo text. Next to the text variable, in the bind option, set get current health. Save and compile. And for the progress bar, we will change its percent binding to get current health. Save and compile. And we can close our gameplay HUD widget blueprint. Now we are going to prepare our game mode. Go to C++ classes, and in the public folder, we're going to add in a new class as well as a new folder structure. Right-click and select New Class. Select Game Mode Base, select Next, and let's name it GM Gameplay. The folder structure will be /game modes. Select Create Class. Let's fix our source file's pathing to the header file by adding in game modes /. Then we can close our game modes class since we won't be needing it currently. And let's jump back into Unreal Editor. And in our game modes folder, we have our new class. Right click and select it. Select Create Blueprint Class based off of GM Gameplay. Select Blueprints, and let's name it GM Gameplay BP. For its default HUD class, we also need to create that. So in our UI C++ classes, let's create a blueprint class from our generic HUD. Right-click, select Blueprint Class based off of generic HUD, and let's name it Generic HUD BP. Let's place it in the Blueprints folder and create Blueprint Class. Let's set its Gameplay HUD class to Widget Gameplay HUD _ WB. Save and compile. Let's close that, and let's set our HUD class to Generic HUD BP, and our default pawn class to Player Character BP. Save, compile, and we can close that, and we can actually delete our player since the game mode will automatically spawn this, but we need to connect our game mode to this level, so we will go to Settings, World Settings, and for our game mode override, we will select GM Gameplay BP. Select Play, and we automatically spawn with our pawn controlling it, but we don't have our HUD, which we will be setting up in the future. The reason why it automatically spawns is because of this player start, which will automatically spawn from our game mode class. In the next video, we will be creating the player's HUD part 3, connecting the player character with the HUD. Welcome to Section 3, Video 8, creating the player's HUD part 3, connecting the player character with the HUD. In this video, we are going to connect the player character to the HUD class and prepare the death and pause functionality. First, we are going to set up the connection to our HUD class in our player character header file. Here we are declaring a pointer variable to the generic HUD class so that we can use it later in the source file, but only in C++, which is why we put it in the private category. We have uProperty above it so that way it can be garbage collected in the event that we need it to be garbage collected. Here we are declaring our functions for pausing and unpausing the game that we can also call in Blueprint. Here we are declaring and overriding an inherited function that is called when a controller takes control of a pawn. This is either when it is controlled by the player controller or when an AI controller takes over this pawn. Let's create our definitions of these functions. Now that we've created our definitions, let's go into our source file and start adding some code. Here we are adding our library for the generic HUD so that way we can call the specific functions within it. Here in our constructor, we are setting our default value for the HUD reference variable to a null pointer. Since this is an inherited function, in the possessed by function, we are calling up the chain for the possessed by function in any inherited functions. Then we check to see if the new controller is a player controller, while at the same time saving a temporary variable from that check if it is valid. So first it'll do this cast, which will check to see if the new controller is a player controller or an AI controller. If it is a player controller, then we save it as a temporary variable and then continue on through the function. If it is not, then we will skip over the if statement. Then we try to get the generic HUD from our HUD class for this player controller, which is a general default sort of function that is automatically supplied with a reference when it is spawned in the game mode. If we did get a successful reference to the HUD class, then we tell it to show the gameplay HUD class by calling the function showSpecificMethod. If we did get a successful reference to the HUD class, then we tell it to show the gameplay HUD class by calling the function showSpecificMenu and inputting the gameplay HUD class getter function, which is one of the getters that we set up earlier in that class, and then telling it to use only the game mode for our input mode and don't show the mouse. In our pause game function, we are attempting to get the player controller the same way we did with the possessed by function, and then saving it as a temporary variable, then checking if our HUD reference variable is valid, or if it's invalid, then we try to cast and get it again, and then we do the check again to see if it is valid. If it is valid, then we show the specific menu, which is our pawn menu, which will fail because we haven't set this yet, and we will do this in the future, but it is good to set this up now. Then, while using the player controller reference that we locally saved earlier, we are telling it to pause the game and then inputting the true value, which will turn pause of the game. And if you put in false, then it would unpause the game. Here in the unpause game function, we are doing the same thing that we did with pause game, but in a different sort of order of operations, where we unpause the game, then we check if our HUD reference is invalid as a sort of check and sort of edge case, which means this may not happen, but just in case, let's do this anyway. And then tell it to show our gameplay HUD class, which will succeed because we've already set this. Now we are finally starting on death implementation, which isn't finished, which we will fill out the rest of in the future, but right now we are just setting up the menus for it. So we are checking to see if our HUD reference is invalid. If it is invalid, then we try to get the player controller and then try to get the HUD reference from that. But if it is valid, then we just skip over this if statement, check if this is valid, and then show the specific game menu, which is the dead menu class, which we will also set up in the future. Let's save all, and then compile our code by going to Build, Rebuild, Project, and let's jump back into the Unreal Editor and hit play to test this. As you can see, we can shoot, we can move around, we can jump. While holding the shift key, we can sprint, and releasing it stop sprinting. To turn off infinite ammo, let's go to our blueprints, in our player character blueprint, in our class defaults, under the gun category, ammo, let's uncheck unlimited ammo, save and compile, hit play, and as you can see when we fire, our ammo counter goes down. And now we cannot fire anymore. In summary, for this section we have created the player character's code and created the player's HUD. In the next section, we will be creating gameplay elements. Welcome to Section 4, Creating Gameplay Elements, Video 1, Setting up our Game Mode. In this video, we are going to set our default game mode and editor map, and create our main menu game mode. First, we are going to set our default game mode, and what that is each level automatically creates a game mode, and this is the default game mode. When we went into our world settings and set the game mode override to GM gameplay BP for our gameplay mode, this overrides it specifically for this level that we have opened, and tells the level to create this game mode instead of the default one. Now let's actually set our default game mode to the gameplay game mode so we won't have to override it. go to Edit, Project Settings, Maps and Modes under the Project category, and our default game mode, we will set it to Gameplay BP. Let's also set our editor startup map to Map Gameplay, as this is the map that we were working in currently, and will automatically open up whenever we open the project if this is not already set. Now let's close our project settings, and in our world settings we can actually set it to none and play the level, and now we won't have to override our game mode since it will automatically be created. Press Shift F1 and go into our world outliner, and as you can see, in the level it has spawned the GM Gameplay BP. Stop playing, and now let's create our game mode for our main menu in the C++ Game Modes folder. Right click, select New C++ class, and it will be Game Mode Base as our base class. Select Next, and let's name it GM Main Menu. Make sure the path is in the Game Modes folder, and select Create Class. Now inside of our source file for our main menu class, let's fix the pathing to our header file by adding in game modes /. And now in our header, we can add some more code. Here we are declaring a virtual function that we will override. In this case it will be begin play, and then we are declaring a variable for a subclass of user widget so that we can pick up this widget and to create our main menu, we can place it in the protected category so that way it may be accessed within this class hierarchy. Inside of our source file, we're adding in the library for blueprint user widget because we are adding the main menu widget to our screen, and this means we will have to use the library for widgets so that way we can call the create widget function. Now let's create our definition for begin play. IntelliSense is not allowing us to automatically create it for some reason, so we have to create it by hand. Now that we've created our definition, let's create our widget. Here we are first calling up the chain for begin play, like we should since it is a virtual function. Then we are checking to see if our main menu widget class is valid, and then we are getting the first player controller within the world, since this is the main menu level that we will be creating later, and we'll be using only one player within that level, which is us, because most commonly in main menus there's only one player. Then we are declaring our temporary struct for our input mode to be UI only, and telling that UI mode to not lock the mouse within the viewport, in case if we wanted to click outside of the viewport, or the window. Then we are setting the input mode, and then telling it to show our mouse cursor, and save the temporary pointer for that variable that we created, which is our widget, so that way we can add it to our screen. Now let's go into our gameplay header file for GM Gameplay. Here we are declaring a function that will respawn the player to one of the player start locations within the level. For some reason IntelliSense is not allowing us to automatically create our functions, so we have to do this by hand also. Inside of our source file, in the respawn player function, we are inputting a controller pointer as our new player, and then checking to see if that pointer is valid. Then we are telling that pointer's controller to get the pawn and then destroy that pawn. Then we are telling the game mode, which is using a function that is already created within the game mode base class, and we are just calling it for restart player, which will create a new pawn and automatically take over that pawn with this controller that we have inputted in. The reason why we have to destroy the pawn first is because if the pawn is already created and controlled by the controller, then it will not work, and it will just return null, or will fail to create a new pawn and possess that. Now let's save all and compile, go to build, and rebuild our project. Now that our project has finished rebuilding its code, let's create a blueprint class of GM main menu. Right click on GM main menu, select create blueprint class based on GM main menu, and let's name it GM main menu BP, and let's place it in the blueprints folder. Select save all. In the next video we will be creating our respawning system. Welcome to section 4, video 2, creating our respawning system. In this video, we are going to set up our respawn system within our player and prepare our pickup actor. First, we are going to open our player character's source file, and within this source file, we are going to add some code within our onDeath function. We are first telling it to stop shooting, or don't allow us to shoot because we are dead, and then we are telling our character movement component to stop movement immediately, so if we are moving, then stop it so we can't keep moving by adding the disabled movement function, and then stopping our character from being able to jump. Then we are removing our gun mesh from the arms mesh component, or detaching it, because it's trying to attach to a socket that won't exist once we set the mesh to hidden in-game, as well as our gun mesh. Now let's compile and save. Rebuild project under the Build tab. Now that it's finished compiling, let's actually test this by going into our blueprints, and in our player character BP, open the full blueprint editor, and in the event graph, right click and drag, and then in an open space, right click and enter num-. This is a keyboard event, or an event node, indicated by the red node. This is an event that will fire off code when something happens within the game. Drag out of the pressed execution pin, indicated by the arrow pointing right and the pressed name next to it, and enter apply damage. This is a function that we can call that will execute code for us, indicated by the node being blue. We need a damaged actor reference or pointer to input into this function, so drag out of damaged actor and enter in self. In Blueprint, the variable self is C++'s version of this, the keyword this. So if we enter this, it will point to our reference variable for self, which is pretty much the same thing. For our base damage, we will set it to 25. Select save, compile, and select play, and let's test this. Press the num-, and if you don't have this, you can always change it to another input key. And as we're pressing it, our health is going down, and now our arms mesh is gone, as well as our gun. We cannot shoot, and we cannot move or jump. Now let's use our respawn system by calling from our onDeath function that we have set up to be a Blueprint native event, so that way it would have a C++ version and Blueprint version of the code. Right-click in the event graph, and select onDeath. This will fire off whenever we call the onDeath function within C++ or Blueprint. Now, this will only fire off from Blueprint code, and this will override our C++ code if it's ever placed within the event graph. To call our C++ version of the code, right-click on the event onDeath node and select Add Call to Parent function. This will call the C++ version of the code, and connect the two execution pins from onDeath to parent onDeath, and now compile and save and hit play, and it still does the same thing. To break a connection, hold the Alt key and left click, and it will break this. Compile and save and hit play, and as you can see, our health going down below 0 doesn't cause our arms mesh or a gun to go away. We can still shoot, but when we connect them, it goes back to the way it should be. Now we are going to set up our respawn system by clicking the event graph, get game mode. This is a function that will only return information or data and does not execute any code, indicated by the green node instead of the blue node. Apply damage will actually execute code, while get game mode doesn't execute code, it just returns a value, or a data, or a pointer. Drag out of the return value for get game mode and type in cast2 GM gameplay BP. Connect the two execution pins from onDeath to cast2 GM gameplay BP, and what this will do is Blueprint's version of casting, where we input an object to check and see if it's our GM gameplay Blueprint version. We can also cast to a C++ class as well, but we're just going to do it for Blueprint for educational purposes. we can drag out of as gameplay BP as a sort of temporary variable and enter respawn player. Respawn player is the C++ function that we created within our GM gameplay C++ class, but because in the U function we made it blueprint callable, this allows us to call this function, and it will call the C++ code that we created without actually having to make any blueprint code. Now we need a new player to input, which is a controller object, which if we drag out of this and enter get controller, this is an already created function within all pawns that will return the controller for this actor. If you want to be able to change the execution route or cable to another node, hold Control and click and drag from that one, and you can drag out of that and connect it to another one. Select Save and Compile and hit play, and now when we run out of health, our player respawns to our new location. We will test this again in another location so you can see the difference. Our player has been destroyed and then respawns at the player start location that we have set within the world. Now let's create our pickup actor C++ class as well as the new folder path. In our C++ classes, under the public folder, right-click and select New C++ Class, select Actor, and select Next, and we will name this Pickup Actor. Our folder path will be /gameplay elements. Select Create Class, and in our source file, let's fix our path to our header file for our pickup actor by adding in gameplay elements /. In the next video, we will be setting up our pickup system. Welcome to Section 4, Video 3, setting up our pickup system. In this video, we are going to set up our pickup system and set up our pickup actor. Within our C++ classes in the gameplay elements folder, we are going to open up our pickup actor. Inside of our pickup actor, we will not be using the tick or begin play functions, so we can just delete them. And in our source file, we should also remove the tick and begin play definitions, as well as the primary tick can never tick line of code, since we won't be ticking for this actor. Here we are declaring a sphere component, which will be our collection sphere, as our root component. Then we are declaring a protected function for when this actor is collected, as well as passing in a pointer of the player's class and naming it collector. We are also making this a blueprint native event so that we can make a blueprint class and have it fire their own version of code that we want to occur when this actor is collected, instead of it making only C++ code occur. Finally, we created a private function for when the collection sphere overlaps or enters the overlap for something that can overlap it. The reason for the large amount of input parameters is because when something is supposed to overlap another actor or component, it is called via a delegate. And a delegate is like a sort of connection between the functions that can be changed or fired, etc. So if we have a delegate for when the player jumps, then we can say when the player jumps, call a function that spawns a cube or rotates an object or whatever. And basically we can remap any function that has the same return type and input parameters for that specific delegate. So when the player jumps or something, we want to rotate a cube, and we have to input a rotator. And that's all we need to know, is the function has to have an input for a rotator only, and that's it. And we can just bind it to that and just fire off the delegate, and we don't have to explicitly call that function. Whenever you need to bind a function or delegate, you must have the ufunction macro above it, or else it will not work. Even if it has nothing within the ufunction's parameters, it must have the above function, or else the compiler will not recognize it and throw an error. We will look at how delegates are set up momentarily. Now let's create our implementations of our functions for the onCollection implementation and onSphere overlap. The word implementation and definition are used in the same sort of context for most programmers. Inside of our source file, we are including the libraries for our player and the sphere component, since we are going to use these libraries within this class. Here we are setting up our root component to be our collection sphere component, while also creating that subobject within one line of code. Then we are setting the collision response to ignore all channels first, and then after that we are setting the collision response to only overlap with pawns, and makes it easier for the physics system to register less actors going through it at once. Then we are binding that delegate to our onSphere overlap function, and now if we right click on the onComponentBegin overlap, which is the delegate, and select Go to Definition, it will bring us to the primitive components header file within the engine, and we can actually select the fComponentBegin overlap signature, which is the actual delegate's sort of class or macro, highlight it, and select Control F on your keyboard, and this will show up any sort of references or when it's been called or used within this whole file. And in this case, it was used on line 145, and this is our delegate, which is a Unreal specific macro that has been created by the compiler to register this sort of stuff, where it will look for anything with this sort of signature as the name of this delegate, and in this case it takes in 6 parameters, and each parameter has to have the class type or input type, and then the name of that input, which in this case is uPrimitiveComponent pointer, and then the name of that sort of input, which would be the overlapped component. And we could actually highlight all of this, copy it, and then go into our header file, and when we're declaring our function, just paste it into the parameters, and then remove the commas in between each of the class types or input types, and then the name of that, but we don't remove it past the name of the input type. When we're doing the add dynamic, it is something within the Unreal Engine specific macros that allow us to bind a function that has the same sort of inputs as the onComponentBegin overlaps signature needs. We're inputting a object, and then we're inputting the function that should be within this object as a direct reference using the AND symbol. Here we are just going to destroy this actor when we call the parent function within Blueprint for onCollected, because we won't be doing anything else within C++ for this actor when it is collected. Here we are using the input parameter of the other actor from our function, and we are casting for the player class, and then saving it as the player, checking to see if it's valid, and then calling the onCollection function, and then passing in that player. If it's not valid, then we aren't collected, and then it will just move on. Let's save all, select Build, and rebuild the project. In the next video, we are going to create our pickups. Welcome to Section 4, Video 4, Creating our Pickups. In this video, we are going to create our pickup actors and prepare our destructible actors. First, we are going to set up our destructible actor by creating a new C++ class within our Gameplay Elements folder. Select New C++ Class, and it will be of type Actor, and we will name this Destructible Actor. In our source file, we're going to fix our include file path by adding gameplay elements /. Now in our header, we can actually remove the tick function, since we won't be using it, and do it the same thing as well within the source file. Inside of our constructor, we won't be ticking at all, so we can actually remove the b_can_never_tick line of code. Here we are declaring a static mesh component, which we have named mesh, and this will be our root component for this actor. Here we are declaring a blueprint native function for when this actor's health reaches 0 and should be destroyed within C++, and we made it blueprint native event so that way we can use it within Blueprint as well. Let's create a definition for our on-death implementation, and let's go into our source file. Here we are declaring our libraries to use for this actor, which in this case is the static mesh component, so that way we can use our static mesh component, and engine minimal, which we'll be using later on. Inside of our constructor, we are setting up our root component to be the mesh component named mesh, and then creating that default sub-object all within one line. And then we are setting its collision object type to world dynamic, which is the collision channel that the physics engine within Unreal is able to register this object as. So if we have another object that collides with it and we tell it to ignore world dynamic objects, then it will ignore this actor and just continue on. We can also allow it to overlap and just block it, which is pretty much normal collision. Now let's go to build and rebuild our project after saving all. Now that our hot reload is finished, let's create a blueprint actor based off of the destructible actor, and let's name it Barrel Destruct BP. And let's place it within the blueprints folder and select our mesh, and let's change its static mesh to a cylinder. We will also change its material to something that's more pleasing to a barrel. I will pick metal steel, but you can pick whatever you want because this is aesthetic, so it's whatever you want. Save and compile. And let's add another component, which will be a particle system. But we will be doing this within the event graph by spawning the particle. So right click and select Event on Death. And we will spawn a particle system at this location. The node is named Spawn Emitter at Location, which needs a particle system, which will be the P explosion particle. And for our location, we will use Get Actor Location. Now, right-click on Event on Death and select Add Call to Parent Function. This will call the C++ version, which will handle all of the destruction of this actual actor. Save, compile, and now we can close this. Let's reorganize our folder structure in the Blueprints folder by right-click and select New Folder, and let's name it Gameplay Elements. Let's click and drag our Barrel Destruct BP into Gameplay Elements and select Move Here. Inside of our Gameplay Elements, let's create a new Blueprint class by right-clicking and selecting Blueprint Class. Select All Classes, and we can actually search for our Pickup class without having to go into our C++ classes and right-click and make a Blueprint class there. So search for Pickup, our Pickup actor, and let's name it Health Pickup BP. Let's open it, and our collection sphere, we will set its sphere radius to 75. Save and compile, and let's add a component, which will be our particle system, and the template will be pHealth. Save and compile, and in our constructor script, we will be setting the color of the particle system by click and drag it into the construction script graph, and drag out of this and enter in set color parameter. The parameter name will be color, and right click off of param and select promote to variable. Let's name this particle color. Compile, and let's set the default color to green. This is honestly up to you on what color you would want. And then connect our construction script execution pin to our set color parameter, compile, and in our viewport it is green. And now, if we select this little box next to the particle color, it will become an eyeball, meaning it's public, and instance editable, meaning we can edit it if we drag it into the level and such. For our class defaults, we can actually edit the color as well, and as you can see, it updates in real time. In our event graph, right-click and select onCollected, event onCollected, and then right-click on that and select Add Call to Parent Function, and connect our collector to the collector reference, and out of the execution pin, enter in sequence. The way the sequence node works is it will fire off this line of code to wherever it's going on how many nodes are connected to it, and when it reaches the end of the nodes that it can't keep going any further, or it hits a delay node or other kinds of nodes or whatever, then it will go to the next execution pin, and you can add more and more, and it will just go down the line in order. You can remove them by right-click and select Remove Execution Pin. connect the then1 to the parent on collection, so this will handle destroying the actor after we've done what we needed to do. In this case, we will drag out of collector and select set current health. Let's connect the then0 node to our set current health, and out of the collector, let's get the max health. And let's connect the return value to new health. Compile, save, and now we can actually duplicate this by right-clicking on Health Pickup BP and select Duplicate. We will name this Ammo Pickup BP. Let's open that up, and as you can see it has the code that we already wrote, but let's change the current health and get max health to setting the ammo. So drag out of collector and set current ammo, and let's get the max ammo. Let's also change our particle system to the P assault rifle ammo particle system. And let's also change the color, let's say to blue or red, whichever you prefer really. Compile and save, and now we can actually close these tabs, and in our level we can drag them into the level. And let's test it by hitting play, and let's shoot to get rid of the ammo in our top right, and let's walk over it, and it destroys our pickup, and our ammo is back to 10. And if you also remember, we use the minus key to subtract health, so when we go to health, it refills our health and destroys the actor. In the next video, we will create our destructible items. Welcome to Section 4, Video 5, Create our destructible items. In this video, we're going to finish our destructible actor. Let's start by opening up our destructible actor's header file. In the protected category, we are going to add in some code. Here we are declaring a virtual function, which will be our take damage function, which is the same function that we used within player character because it is inherited from actor, and this occurs automatically whenever we apply damage to an actor. Let's create our definition really quickly. We are also setting up our damage values for when this actor explodes and should damage any other actors, as well as our health values, which will help us know whether this actor should die and explode. Inside of the constructor, we are going to set our default values. Here we are declaring our default values for the damage radius and strength, or the damage amount, and health variables, as well as our max health and current health. Inside of begin play, we are just updating our current health to max health like we've done previously in the player character. Inside of our take damage function, we are doing the same thing that we did with our player character's take damage function, which is just a bunch of checks to see if we died, and if not, then subtract health. So inside of our onDeath implementation function, we are doing is first preparing an array of overlaps. The reason why we're saving an array is because we're going to overlap multiple objects for this actor when it explodes. When it explodes, it should damage any actors that are within the radius, so for each actor we overlap, we have to have an overlap struct for that actor. Afterwards, we save the mesh's component location within the world as our start position, and this is where the mesh will be located within the world. This can be done with the same effect as get actor location, but we're using a components location to show that there are multiple ways of doing one thing. Then we are saving a shape, which is a struct that we specified to be a sphere with a radius of our destruction radius variable. Then we trace for multiple overlaps that overlap the world dynamic channel, which in this case will be the player and this destructible actor. The reason for why we had this function within an if statement is because it returns a boolean for if this hit anything at all, then return true, otherwise return false. This will also return the boolean after it's finished tracing, so it won't stop at the first overlap, because at that point it would be a single overlap function and not a multi-overlap function. The fquat identity is a bit of vector math, which in simplistic terms is just a rotation with x, y, and z all set to 0. So if we hit anything, then we loop through every overlap that occurred, which we have inputted, into the parameters of that function for multi-overlap by channel. And if we hit anything, then iterate through the array and apply damage the same way we did with our player character's code, except instead of point damage, we're just using a general damage vent, since we aren't using a specific point of damage. And then finally, we are destroying this actor after it's applied all the damage and everything, and moving on. Let's save all, select build, and rebuild our project to compile it all. And while that's compiling, let's actually bring our gameplay elements barrel destruct BP into the level, which is in our blueprints folder. Since it has finished compiling, let's test it by hitting play and shooting the barrels. As you can see, it destroys the other barrel, which is what we wanted, and it destroys itself and damages us. In summary, we've set up our game mode, we've created our respawn system, created our pickups, and created our destructible items. In the next section, we'll be creating our menus. Welcome to Section 5, Creating Our Menus. Video 1, Setting up our main menu widget and level. In this video, we are going to prepare and design our main menu widget and create our main menu level. First, we are going to create a new widget blueprint inside our widgets folder, and we will name it main menu WB. Now, before we start designing the main menu, we are going to create a new level and name it map main menu and organize it in a levels folder. So, in our content folder, we'll right click and select new level, and we'll name it map main menu. And we're going to also right click and select new folder and name it levels. And we'll click and drag the map gameplay while holding control. We can multi-select objects or assets and drag them into the levels. We'll move here, and now we have our levels in here. Let's open up our main menu level. Let's save selected, and as you can see, nothing is in here, which is what we want. Now, inside of our project settings folder, or if you want to go to edit project settings, in the maps and modes tab, our game default map we're going to set to our main menu. This will open up this map when the game starts automatically. Now we can actually start designing our main menu, so let's close the project settings, and inside our widgets folder, in the main menu widget blueprint, let's compile and save. And so for the main menu, we're going to have two buttons that will open the level, which will be a open level and a quit button for quitting the game, as well as some text letting us know that this is the main menu. So first, let's start on that main menu text by bringing in from the comment folder or category. In the palette, we're going to drag in a text into the widget designer or viewport, and we're going to set its anchor to the top middle, and we're going to set its position to 0 in the X and 150 in the Y. We're going to change its text to main menu, and we're going to change its alignment to 0.5 in the X and leave 0 for the Y. We're also going to check size to content, which will resize the actual text box to the text letters, and we're going to set the size to 50. Now let's drag in something called a vertical box. Inside of our palette, let's search vertical box. Let's drag that into the viewport. We're going to set its anchor to the center, and then we're going to set its position to 0 in the X and 150 in the Y. Our size is going to be, for the X, 1000, and in the Y it's going to be 400, and the alignment will be 0.5 and 0.5. We don't need the size to content, as this is what we want, which a vertical box will vertically align any widget components that are attached to it as a child. So if we dragged a text under the widget vertical box, it would automatically align it to a specific position vertically, and it orders them accountable as well. You will see in a moment. We're going to add in a button and drag it under the vertical box like so, and as you can see, it automatically created one, and placed it at the top of our vertical box and automatically sized it. We're going to rename this button to our Start button. You can right click and select Rename, or you can select F2 on your keyboard. We'll name this Start button. And we can also drag text into the Start button. And as you can see, it shows up and automatically resizes the text to be in the center. For the text, we're going to tell it to be Start Game. We're also going to change its color from color and opacity to black, so that way it's easily visible. We're also going to set its size to 40, and as you can see, the button resized automatically. And if you select the button again, let's change its size from auto to fill, and it will fill out the vertical box. We'll be adding to it, so that way it's not completely filling up the screen. Now, right click, copy, and then select the vertical box, right click, and paste, and it will add another button. This one will be our Quit button. So we're going to rename the button to Quit button, and we're going to change the text to Quit to Desktop. And as you can also see, the button originally that was filling up the entire vertical box now is resized to be halfway, but it's vertically the one above the Quit button. And this is because we have it arranged that way. If we move this one to be above the Start button, like so, it automatically reordered it. And we can use these arrows as well to reorder it again. Now let's add some space to these buttons so that way they're not so close. Inside the palette, let's search for a spacer. And let's drag it into the vertical box, in between the Start button and Quit button, and select the spacer, and let's set its Y to be 150. And now they're spaced out, which it looks pretty good. It's very simple, you know, something to set up. You can add more to this if you choose to. You can change the images for the buttons by going into the style, and they have specific images for normal, hovered, pressed, disabled, etc. You can change the color, etc. That sort of thing. You can look up documentation on changing the UI and designing for the UI inside of the Unreal Engine documentation page, which is freely available on the internet. Now let's save and compile, and now we can actually test this temporarily by going into our map, main menu, in Blueprints in the top toolbar, select Open Level Blueprint, and in Begin Play, let's drag out of this and select Create Widget. We will select the main menu widget blueprint and then drag out of the return value and add to viewport. This will be temporary, so we can just at least test this. So select Compile, Save, and in our viewport, let's hit play. And as you can see, the buttons showed up, but we can't actually press them. Let's add the option to show the mouse by Get Player Controller. This is all temporary, by the way. We'll be removing this in the next video. And drag out of the return value and select Show Mouse. For Set Show Mouse Cursor, and let's checkmark that to set it to true. Connect that to the Add Viewport, compile, save, and let's hit play. And now we have our mouse and we can click the button and it works. We also have the other UI because we are currently using the default game mode, which will automatically spawn the player, which will automatically also spawn the other UI. Let's actually clear this up now, since we tested that the buttons are set up and they work. In the next video, we will be adding functionality to our main menu widget and our level. Welcome to Section 5, Video 2, adding functionality to our main menu widget and level. In this video, we are going to add functionality to our main menu's buttons and have the main menu level spawn our main menu widget automatically. So first, we are going to set up our level to spawn our main menu widget. Let's open the world settings, and if you don't have it already open, inside of the settings, world settings, it shows up. Under the game mode tab, for our game mode override, we're going to set it to our GM main menu, BP. Now let's open that game mode. you can find it easily by selecting the eyeglass, which will automatically find it within your assets, and then we can open our blueprint. So you may see we already have a main menu class variable for this blueprint, and we haven't set it yet. We're going to set it to our main menu widget blueprint. Let's compile and save. And now, since we already connected our level for map main menu to automatically override the game mode to be our blueprint game mode that we just edited, it will automatically spawn that main menu widget. So if we hit play, now it's already spawned it. Inside of our widget for the main menu, let's open up the widget, main menu WB. Let's add some code to work for our start game and quit to desktop buttons. Inside of the graph in the top right, we have pre-construct, construct, and event tick. Pre-construct occurs only within the editor, which we will not be using, and typically is not something that people use, unless you're testing something out. So we can delete that. We also can delete event tick. Event construct is the widget version of when this begin play, but only for this widget when it gets shown onto the screen. In this case, what we want to do is right-click in the graph and get owning player. You may see two versions, either one will work. Drag out of the return value, set show mouse, and let's set it to true. So that way the mouse cursor will always show when this widget gets shown on the screen. The owning player is a player controller variable or reference that widgets automatically have when they are created. Now we're going to add the start game button to work and open up our level. In the variables, select start button, and at the very bottom of our details panel, you'll see on clicked, on pressed, and on released, unhovered. These are all events that will fire when a mouse interacts with the button. So for the start button, it has its own set of these events, and the quit button also has the same events, but for itself. So for our start button, we're going to select on clicked, and it automatically creates the event within the graph. Let's drag out of the execution pin and enter open level. This will have to be an exact copy of what the name of the level is, which in this case will be map underscore main menu. So we have to enter that. If this is incorrect, then it just won't open the level and it will probably give you just an error within your output log telling you that this is not a valid map or level. For the options, we don't need to fill out anything else, so we can keep that minimized. And our start button is ready to go. Now let's add the quit button functionality for on clicked. And let's copy our get owning player by selecting it and pressing Ctrl W to duplicate this and place it where our mouse is within the graph. Let's drag out of this and enter an execute console command. Hold Alt and left click to break a link. We don't need the world context object, so we can delete that and probably just drag out of the onClicked and enter an execute console command. And now we don't have that, but it needs a specific player, which in this case would be our owning player, because this takes in a player controller, and this is our player controller. For our command, we just enter the word quit. It doesn't matter if it's lowercase or uppercase, it will just run the execute command of quitting the game and closing the application. So now our menu is pretty much set up. Let's save, compile, and let's test it, but without having to go back into the viewport. Next to the play button is an arrow, which allows us to open it in different ways. For our new editor window, that allows us to create a new window altogether. Instead of having to play it within this, we can select new editor window, and it will allow us to drag it around and move it around and resize it to check and see if the widget works correctly, which it does. It should automatically resize like it is doing now. We can select quit to desktop and it should close this, and it does. The other options for mobile preview ES2 is for mobile games like Android, iPhone, etc. Standalone game is making a version that is supposed to run like when you build the game. This is what it should be like. And simulate just doesn't run the game mode where it runs spawning the player. So it will run the game, except it just won't spawn the player. For multiplayer options, we don't need to talk about these currently because this is not an advanced course for multiplayer. If you go into the advanced settings, This allows us to change the new editor window size that it is by default, our standalone games window size, etc., number of players, that kind of thing. So when we play it in a new window, the quit button works, we select start game, and it does not seem to open. That is because we are opening the same menu that we are already in. So let's fix that. In our assets, in the levels, we have map gameplay. In my opinion, the easiest way to just get the name is just change it like so, and then copy, or press the F2 key to start editing it and just copy the name, that kind of thing, and just go back and paste it. In our case, it is map gameplay, or whatever the name of the level is that you use, or that you are using. Compile, save, hit play, start game, and we're able to play our game. And we can hit escape, and we're still in the main menu level that we started in. In the next video, we'll be setting up our level ending actor. Welcome to Section 5, Video 3, setting up our level ending actor. In this video, we are going to set up and create our level ending actor. So first, we're going to create a new C++ class of type actor in our gameplay elements folder. It will be of type actor, and we will name this level end actor. So first, let's fix our source file's include path to our header file by adding in gameplay elements /. And at the same time, we can also remove this primary B can never tick line of code because we won't be ticking in this actor, as well as removing the tick function altogether and the begin play function. So inside of our header, we are declaring a box component and a uBillboard component, and using the billboard component as our root, or naming it root, and our box component as our collision box, which we will be attaching to our root. The reason for why this is a billboard component is because these components are like scene components that can be easily seen in the editor and selected, and it's a sort of ease of use component, which you will see after we compile it and bring this actor into the level. It is not visible in the game, but it is visible in the editor. Here we are declaring an fname variable, which is similar to a string and text variable, but they are different for specific reasons. The main differences between string, name, and text variables are that texts are 40 bytes of memory, but they can be modified in code, such as adding to the current text and such, and localizing automatically. Strings are 16 bytes, but can be modified and are not case sensitive, while names, which is our level to go variable, are 8 bytes and cannot be modified and are case sensitive. So once we confirm a name, we cannot actually append to it or remove specific characters from it. We are stuck with the name that we have given it, unless you want to reset the whole thing, which is just make it equal to a new name. Here we are declaring our overlap begin function for the collision box component. So when we overlap the player, open the level to go to. Let's create our definition for on-back begin overlap. And let's go into our source file and start adding some code in there. Here we are just adding the libraries for the two components that we are using, as well as the player's library and the gameplay statics function library. The engine.h file, which we are using, is a smaller version of the regular engine.h file, which would cause IntelliSense to load much slower and have a bunch of other extra code that we won't be using or needing. So this is a sort of smaller version that Unreal or Epic have made specifically for this purpose, for faster development and such. Inside of our constructor, we are creating and setting our billboard component as the root component, and then setting the root component in the same line. Then we are creating our collision box, and then attaching it to our root component, or the root, and then binding our onComponentBegin overlap dynamic delegate to our onBox overlap begin function. And then we are setting the default level to go to name to a generic string, which will be map name. So here we are actually checking if the other actor is a player by casting, because casts can also return the Boolean value, or they can also return a pointer, and if the pointer is valid or not, then we'll continue in this if statement. So this is a sort of Boolean if we choose to, which will return either success or failure if this other actor, which is an input parameter, if this other actor is of type a player character, then it will continue into the if statement. If not, then we will skip over it and nothing will happen. Then we are checking if our level to go to is a valid map. So what we do is we convert it to a string by adding the .toString, which is a function, and saving that as another string variable called mapName, and inputting that into this function, which is within the engine for checking if a map is valid or not. If it is not valid, then we print out a debug message and then exit the function. But if it is valid, we'll skip over this if statement and not run any of this code and just open the level like we are supposed to. Now go to build and rebuild our project, and we'll test this in the editor. Now that it's finished compiling, let's test this by, instead of creating a blueprint class of our level and actor, we can just actually click and drag it into the level, because these are C++ actors, where we won't be inheriting from blueprint, we'll just be inheriting straight from the C++ actor, and thus it mitigates sort of extra work that we have to do. The reason for why we did it with a bunch of the other actors is because we made different versions or we edited some values, that sort of thing. If you're just going to drag it into the level one time for that one level, just drag it in there from the C++ class instead of making a blueprint class, for ease of use. I'm going to place mine around this table, and then to edit the box size, we can go into the components in our details panel and select the collision box and actually change the box extent in the X, Y, and Z. Make sure to select the base instance so that way we can move around the whole actor, or you can deselect the whole thing by hitting the escape key and then selecting our billboard, which makes it much easier to select than just selecting these box lines. Let's change the name to our map main menu. And if we hit play, and we walk over to the table, or where you put your box, it loads the main menu, and I can quit to desktop and it will close the app. Now what if the map is incorrect? Let's test that. I'm going to reset this back to default, because I still have it saved in my clipboard so I can paste it back in. Currently it says map name, so it should not exist. And as you can see as I close this, inside of our output log, we can see a warning saying, warning, map name does not exist. In the next video, we will be setting up our pause menu widget. Welcome to section 5, video 4, setting up our pause menu widget. In this video, we are going to create and design our pause menu widget and design our dead menu widget. First, we are going to create a new C++ class from user widget and place it in the UI folder. When we create a new class, let's select Show All Classes and enter in User Widget. We will name this Pause Menu. So what we're going to do in a future video is we're going to link a button press to a function within C++ via the Pause Menu C++ class. Let's fix our source file's include path to the header file by adding in UI/. Now that our code has been compiled and ready to go, we are going to start designing our pause menu. Inside of the Blueprints folder, under Widgets, let's create a new user widget by right-click and select User Widget, Widget Blueprint. We will name this pause menu WB. Inside our pause menu, we're going to add an image to the canvas panel, and we're going to name this background. For our anchor, we're going to select fill screen, which is in the bottom right, and set our offset right and bottom to 0. We will also set our color and opacity to black, and a transparency of about 0.25. Now we're going to add a border to the canvas panel, and we're going to add text to that border. For the anchor of the border, we're going to set it to the top middle, and its position will be 0 and 150. We will set size to content to be true, and we will set the brush's color to black and a transparency of about 0.5. Now let's select our text block, and we will change the text to paused. And we will change the font size to 75. Let's also adjust our alignment to 0.5 on the X to even it on our screen. Let's hit save first and then compile. And now we are going to add a vertical box to the canvas panel as well. The vertical box's position will be 0 and negative 105, and the anchor will be in the center. Let's fix our position back to 0. Our alignment will be 0.5 in the X. And for our size, we will use 400 and 400. Now we are going to add a button to our vertical box. And this is very important, to name it Resume Button. Let's also add some text to that button. And let's change the color and opacity to black. And let's change the text to Resume Game, as well as set the font size to 30. Or our Resume button, let's set the size to Fill. And let's copy the Resume button and paste it in the vertical box twice. The second one will be named Main Menu Button. It is important to correctly name it, and also that includes capitals. And for the third button, we will name it Desktop Button. For the text of Main Menu Button, we will set it to Quit to Main Menu. And for Desktop, we will set it to Quit Desktop. Now we will add in 2 spacers to our vertical box, but we will place it in between the Resume button and the Main Menu button for the first one, and we'll set its size in the Y to 75, and we will copy that and paste that in the vertical box as well, and place it between the Main Menu button and the Desktop button to space them evenly. Save and compile. And let's go back into our map gameplay so we can access the content browser, and right-click on Pause Menu WB and select Duplicate. We will name this Dead Menu WB. Now we are going to change our paused text to You Are Dead, as well as change the Resume button to be Respawn Button, and change our text to Respawn. Let's save and compile, and we can close the Dead Menu WB, but in our Pause menu, go to the Graph, and in the Class Settings, we're going to change the parent class from just User Widget to our Pause menu User Widget. Compile and save, and we're good for now. In the next video, we will add functionality to our Pause menu. Welcome to Section 5, Video 5, adding functionality to our Pause menu. In this video, we are going to add functionality to our Pause menu and Death menu, and connect our player character to our Pause menu. So first we are going to open up the player's code and connect our Pause menu to our pause game function within the player's code via the inputs. Let's open up the characters folder in our C++ classes and open up our player character. Inside of our source file, in the player input component, we are binding the action for pause game when it's pressed to the pause game function. Here we are just binding it for our player for when it's pressed, and the reason for why we didn't bind it for unpausing the game is because when we call the pause game function, we are calling to change the input mode to UI only, which blocks key input from our player controller, but not the mouse, and is used for UMG only. When we are in game mode only, then the player controller doesn't block any inputs, and there is also a game and UI input mode that allows for UI and key input to be used at the same time and also be used for UMG in the game, and doesn't block input either. Now let's open up our pause game file in the header and source file. So inside of our header file, we are first declaring and overriding a virtual function that is protected within the user widget class that returns a boolean named initialize. This occurs when we select the compile button within the blueprint editor in the Unreal Engine, and it will return true if we compiled successfully and false if we didn't compile successfully. Then under the private category, we declare a bunch of variables and functions. Honestly, it's going to be 3 variables and 3 functions. Starting with the resume button pointer variable, it is of type uButton, which is a subclass of uWidget. We have a uProperty with the meta tag bind widget, which means it will search within this UMG widget and see if any buttons have the same exact name as the variable's name, and it is case sensitive. So in this case, it'll search for resume button with the exact same camel case written name. If it didn't find a button with this variable's name, then it will give an error when we compile in the UMG widget until we find a button with the same name. Then we have a function for when this button is clicked, which in this case is onResumeClicked, which we are going to bind to a uButton specific delegate named onClicked for the resume button. And we will repeat this same format twice for the desktop button and the main menu button. Let's create our definitions really quick. Now that our definitions have been created, let's go into our source file and fill out those definitions. Here we are including our libraries for the button, which is located in the components folder, and the uGameplayStatics function library, and the player's library, so that way we know this is the player, and we have some sort of context of the player. Inside of our initialize function, first we are calling the super function of initialize, which will return a boolean and check if it is false. So if the parent version of initialize failed, then there is no point in continuing and return false, since if our parent failed, we're probably going to fail being created or something or initialized. So if the parent version did not fail, then we check if the UMG widget properly found the resume button and the desktop button and the main menu buttons through a valid check for each one, and then we bind the onClick delegate for that specific button, which in this case would be resume button for desktop, and main menu button would be separate, and we bind it to their onClicked functions that we created, which for the resume button would be onClicked for onResumeClicked. And we just repeat this for every button that we need to bind in C++. And then finally we return true and exit the function since we are finished and successfully did everything that we need to do when we are initialized. Inside of our onResumeClicked, here we are getting a reference to the player class, similar to how we did in the widget gameplay class, and then we check if it's a valid reference, and then if it is, unpause the game. Here we are calling the console command quit the same way we did within our blueprint for the main menu, but in this case it is in C++. The difference between getOwningPlayer and getOwningPlayerPawn is that it returns a pawn for the owning player pawn, and the getOwningPlayer returns a player controller. Inside of our onMenuClicked function, we are just opening the level explicitly to map main menu. Now, if you wanted to make this a variable instead of explicitly typing it in, you may refer back to our level ending actor class, which does it the exact same way. Now let's save all, select build, or actually let's do this in C++ in our Unreal Engine editor. Let's open the Unreal editor and select compile. While that's compiling, let's go into our blueprints folder and open up our player character BP, and let's remove onDeath code that we wrote in blueprint and select compile and save, since we now have our onDeath menu so we don't need to respawn the player automatically anymore. We can close that. Let's open our generic HUD blueprint, and let's bind our dead menu class and our pause menu class to their widget classes. For dead menu, we will use dead menu WB, and for pause menu and our compile finished, we will use the pause menu WB. Compile, save, and let's close that. And inside of our widgets, let's add our functionality to our dead menu in Blueprint for time's sake. We can delete these 3 starting nodes and select our respawn button within the variables graph and select onClicked in the details panel, and it will create that node for us, and let's repeat that for the main menu and desktop button. For our respawn button, we will get the game mode, drag out of the return value and cast to our gameplay game mode, and we will call the function respawn player. Apparently we are just getting the owning player. For our main menu button, we are just going to open the level main menu, or map main menu. And for our desktop button, we can actually grab the owning player again, right click and enter an execute console command, and connect our specific player to the owning player, and call the command quit. Let's save and compile. And let's test this by hitting play. And our backspace key should also open up the pause menu, and it did. We can select resume game, and now we can play the game again. If I close this and play this again and subtract our health all the way to 0, we die and we can't move around or look around or anything like that. So we can respawn, and when we die again, we can quit to the main menu, we can start the game, pause it, quit to main menu, start game, pause it, quit to desktop, and it all seems to work. So in summary, we've set up our main menu and level, created our level ending actor, and set up our pause menu and death menu. In the next section, we will be creating interactable objects and shipping the game. Welcome to Section 6, Creating Interactable Objects and Shipping the Game. Video 1, Creating our Interaction System by Using Unreal Interfaces. In this video, we are going to learn about Unreal Interfaces and create our own Unreal Interface. Interfaces are a class that is used by Unreal's C++ as a sort of messaging system between classes for calling functions or specific code. This is similar to delegates, but instead of being a variable, it is an arbitrary function. So say we have a trap, and in the game we have multiple types of traps that are supposed to do different things when set off. So we could go through the route of inheritance and override a virtual function and so on, or we could use interfaces to do something similar. And in this case, it would possibly help with performance, or it would just be another way of doing the same thing for other reasons. But interfaces allow us to create a class such as an actor and inherit both from actor and the interface class at the same time. And this is the special thing about interfaces, which is that they can be attached to already established classes, which can help in development later on. So in an interface, we would declare a function that is either virtual or a blueprint native event without adding a definition, and in another case that inherits the interface, and it would be overwritten and given a definition. Another thing about interfaces is that they can be inherited to blueprint classes or attached to blueprint classes that don't inherit from it already, and they are prefixed with the letter I in C++. In the header file of the class, it contains a uClass and a interface class with the same name, as it's used for Unreal Reflection System to see the actual interface. Now let's actually create the interface inside of our Gameplay Elements folder. Inside of our C++ classes, inside of the Gameplay Elements folder, we're going to create a new class. And this will be of type Unreal Interface at the very bottom. And we're going to name it Interaction Interface. Let's create the class. Inside of our source file for our interaction interface, let's fix the pathing by adding in gameplay elements /. Now inside of our header, you may notice that we have a U class and a general C++ class. As you can see, the U class is named U interaction interface, which inherits from U interface, and our I interaction interface, which is a generic C++ class that exists inside of our game's module, indicated by the purple text reading out the name of our project and adding API at the end. And they already apply some boilerplate sort of comments, and boilerplate means it's just something that usually gets created when this class is created, sort of automatic stuff. Inside of our U interface, we're going to change minimal API to blueprint type. Here we are adding the keyword blueprint type, which allows for interfaces to be used as variables within blueprint code. Inside of our interface, we are adding a function called onInteract, which is going to fire off a blueprint and C++ version indicated by blueprint native event. Now we aren't going to add anything else because this will have the onInteract implementation code and be overridden. Instead of repeating it inside this class, we're just going to override it in any subclasses that use this interface. You don't have to worry about the squiggly lines for our U interface and generated body. That's just IntelliSense not working as properly as intended. There are plugins and add-ons for Visual Studio that can deal with this and not have that problem. But for us to fix it, we have to go back into Unreal, compile, and once it finishes compiling, which it should succeed, go to File, and refresh Visual Studio project. Now that ours has finished compiling, go to File, refresh Visual Studio project, and it will update the code project and generate project files. And inside of Visual Studio, it will ask to reload or reload all, ignore all. I usually select reload all. It might also show override and save as options. Select override, and this will fix those problems. Once you have done that, select save all, so that way it confirms these changes, and these usually take care of it, and usually these types of errors don't really matter or really affect the code in any way. It's just IntelliSense not working properly. In the next video, we will be creating our initial interactable base class. Welcome to Section 6, Video 2, creating our interactable initial base class. In this video, we are going to create our base interactable class. So first we're going to create a new C++ actor of our base actor inside of our gameplay elements folder inside of our C++ classes. We're going to create a new class, and it will be of type actor, and we will name it interactable actor. Inside of our interactable actor, we're going to remove almost all the boilerplate coding except for the constructor itself. So we're going to remove tick and begin play, and the primary tick can never tick line of code. And inside of our header file, we're going to do the same thing by just removing begin play and tick. Inside of our interactables header file, here what we are doing is including the interfaces library so we can inherit from it. When inheriting from a class, you have to have the class's library or else it won't properly inherit from it because it doesn't know what it is. So this would be the way that we actually add the class to inherit from. First we would include the library and then add a comma and then public and then the class name, which in this case is INteractionInterface. Don't worry about the errors, these are just IntelliSense not working properly with the class itself. Inside of the actual class, what we are doing is we're overriding our blueprint native event function within the interface that we've described as onInteract, and since it's blueprint native event, the compiler would search for onInteract implementation, which we have defined inside of our subclass, because by default it would be a pure function, and it doesn't have a definition. So we're overriding it, and because this is the first instance of us using it, in the class hierarchy, we don't need to add the override keyword. Let's add our definition. And inside of our source file, inside of the onInteract implementation, we are printing out a debug message for the interaction being called from the interactor, which would be the player. The way that the UE4 macro or UE log macro works is that it will add a message to the output log window that uses a temporary category, and then we mark it as a warning, which makes it yellow inside of our output log so we can easily see it, and then we actually add the log message, or the message that's going to get displayed for the warning. And here we are also using another coding language called Unicode that Unreal supports by adding a variable to our string by using the %s, which in Unicode it would search for a string that is converted to characters. So it'll search for characters, and what we're doing with the comma afterwards is the interactor get name would return a string, or return an f string, and when we add the pointer, what it does is it converts it from a string to a bunch of characters, and then it will search back into our text macro, which is a bit of Unicode in there, and it will search for any %, and then s, and it will insert that string into that location inside of the string that's already been supplied. For more information on how to use the text and debugging and printing and all that, there is a documentation page on Unreal's documentation website that's freely available explaining about debug messaging. So now let's open up our player's header file, and we're going to also inherit from the interface within our player as well. Here we are adding our player inheriting the interface because we're arbitrarily going to call the onInteract function to other actors, and to do that we have to inherit from the interface for this actor itself. But because of this we would have to add the onInteract function for this class as well, but we don't need to add a definition, which we can also do by just making it a pure function as well. Inside of our protected category, here we are declaring it as before, but compared to our interact actor, we don't need anything to occur on the player, so we make it a pure function. Despite all the warnings and errors, it is just IntelliSense not working properly. We can go back into Unreal and it will compile successfully. As you can see, our code compiled completed, or successfully, and to fix those errors we can actually go back to File, refresh Visual Studio Project, update our code project, which it's going to do automatically for us, and if we jump back into Visual Studio, we're going to select Reload All, and it will reload IntelliSense for us. Let's also select Save All just in case. And as you can see, our errors are gone, including for the interactable actor. In the next video, we will be setting up our sub-interactable objects. Welcome to Section 6, Video 3. Setting up our sub-interactable objects. In this video we are going to create our sub-interactable object and then create blueprint interactable objects without inheriting from our interactable actor. So we are going to be working only in Blueprint for this video, so inside of our Blueprints folder, inside of our Gameplay Elements folder, we're going to add another folder and we're going to name it Interactables. Inside of here we're going to right click, select Blueprint Class. Inside of our search, we're going to search for the interactable actor, which is our custom actor that we created. And we're going to name this blueprint actor Door Interact BP. Let's open it up. And inside of our components, we're going to add in a static mesh. For our static mesh, we're going to set it to SM Door. Let's compile and save. And inside of our class settings, you can see we already inherit the interface for interaction interface. So we already have this set up. So we can actually close the Door Interact BP, and we're ready for that interaction actor. So now we can start on our blueprint actors that don't inherit from the interact actor. So we're going to add a new blueprint class, and it's going to derive from actor, and we're going to name this one Bouncing Cube Interact BP. Now first what we're going to do is we're going to add a cube component, which is just going to be a static mesh, but we already have one set up for a cube, which is pretty much a default thing that Unreal has set up because so many people use cube, sphere, and plane as like basic components. And we're going to click and drag it and make it our default scene or root. And inside of our cube details, we're going to set our simulate physics to true, which is going to change our collision preset to physics actor. If we uncheck the simulate physics boolean, it will set it back to block all dynamic. So we're going to want that true, compile, save, and now what we're going to do is go into our class settings, and under the interfaces category, we have no inherited interfaces and no implemented interfaces. So we're going to add an implemented interface by clicking add and then enter in the interaction interface. Here what we are doing is implementing our interface within Blueprint so that way we can still receive any function within that interface that is being called or relates to that interface, which in this case is the onInteract function. It is important to remember that whenever you implement an interface only in Blueprint, you must compile that blueprint immediately after so that it can register the interface's functions so that we may use it within code. So right now, if we go into the event graph and try calling the onInteract function, it will not work. So we have to compile, and now if we right click and type in onInteract, it allows us to actually use it as an event. But we're going to do that in a future video. So inside of our variables, we're going to add two float variables, one named jump strength, and let's compile the blueprint so we can set the default value to 500. And for our second float variable, we're going to name it hit strength. And we're going to make this default value a very large number, so 100,000. Let's add a bit of some code. So we're going to add the event point damage, which occurs whenever this actor receives any of the Unreal specific damage type, which is going to be point damage. And we're going to drag out the execution pin and add impulse at location. We're going to have the one that has the cube in parentheses, so that way we don't have to click and drag it into the event graph, it's just already made for us. For our location, we're just going to use the hit location. For our normal, what we're going to do is multiply by a float, and we're going to drag the result into the impulse. And for our float value, we're going to drag out of that and multiply again by the int, and we're going to put the integer to -1. And for the float value, we're going to use hit strength. So we can click and drag it and just make it equal b, as it says, which means we just drag it over and it will automatically connect it for us. And we hit compile, no errors. So at this point now what we're going to do is we're going to drag out of the execution pin of the add impulse at location and then draw debug string. For our text location, we're just going to use get actor location. And for our text, we're just going to say, ow, stop it, because this is meant to show that the cube is getting hurt. For our color, let's just change it to something like red. It's easy to see. And for our duration, let's set it to 2.5. That seems to be a very common number, reasonable number. And let's compile and save. So any point damage that we receive will apply an impulse to the cube at a specific location and print out a debug string showing that it was hurt. The impulse is a bit of vector math that uses the magnitude of a vector, which in this case is the hit normal, which originally is facing the player, but when we multiply it by the -1 value, it flips it, so that way it's facing towards the cube instead of away from the cube. And when it's facing towards the cube, it's going to push the cube away from us, which is what we want. And then we increase the amount of strength of that push to our hit strength. We can actually test this by going into the map and dragging the cube into the level. Since it's simulating physics, let's put it above ground since it's going to just fall to the ground. And when we shoot it, it bounces around. And it gets affected to where it got hit. Now what we're going to do is close this, and we're going to add another interact actor, adding the blueprint class. We're going to make it an actor, And we're going to name this NPC Interact BP. So before we do anything, we're going to go to our class settings and implement our interface, which is interaction interface, compile, and we're going to add a scene, and we're going to name this one root. And we're going to make that the default scene. And then we're going to add a skeletal mesh, and then we're going to add another scene, and we're going to name this message location. For our skeletal mesh, we're going to set its mesh to a engine specific mesh that comes with the engine. So we can click on view options and select show engine content, and we're going to use tutorial TPP, and we're going to set the anim class to tutorial TPP as well. For our message location, we're just going to move it up to its eyes, and let's save and compile. And in our skeletal mesh, we're going to go down into its collision and change it from no collision to block all dynamic. Compile and save. In the next video, we will be adding functionality to our sub-interactable objects. Welcome to Section 6, Video 4, Adding Functionality to our Sub-Interactable Objects. In this video, we're going to add functionality to our interactable actors. First, we're going to work on our door interactable, so inside of our blueprints, gameplay elements, inside of our interactables folder, and we're going to open up our door interact blueprint. Inside of the event graph, we're going to add event on interact, and we're going to right click on event interact and select the add call to parent function following the parent version of on interact. And we're going to drag out of the blueprint version and call sequence. And we're going to connect the then1 execution pin to our parent on interact and connect our interactor to the other interactor. And out of the then0 interaction or execution pin, we're going to call flip-flop. Out of A for our flip-flop, we're going to use set relative rotation. And we're going to use our static mesh in parentheses version, which will automatically connect in the static mesh from our components, because it needs a component to set its relative rotation. And we're going to set its Z to -90. And then we're going to just select this again and duplicate it by pressing Ctrl W, and then connect it to B and set our Z back to 0. Let's compile, save, and I'm going to explain what this all should do. So, here what we're doing is when this actor gets interacted with, we're going to first rotate the actor 90 degrees, or the door 90 degrees, and the flip-flop node it will check to see if it already went through A. If it did, then it's going to go through B when it gets called again, and vice versa, which will alternate as the description says. So if we rotated 90 degrees, then rotated back 90 degrees to 0, and then 90 degrees, 0, so on. And every time we interact, since this is a sequence node, it will go to this flip-flop, execute one of these two, and then it will come back to the sequence and then fire off the next execution pin in the sequence, which is the parent on interact, which will just print out a message in our output log for who interacted with it. Let's quickly test this by dragging our door into level. I'll place it right over here. I'm going to rotate it about 90 degrees, and we hit play. And if you pay attention in the output log at the bottom, I should interact with it. The reason why it's not working is because we haven't connected our player yet though, which we're going to do in a future video. So now let's fix our bouncing cube to also interact correctly by opening up our bouncing cube interact blueprint. And here we already have it for when it receives damage. We're going to add a event on interact and drag out of our execution pin and enter in a branch Or if you're just in the regular graph, you can hold the B key and then left click, and it will create a branch for us automatically. Say hotkey for blueprint. Then we're going to drag our cube into the event graph and drag out of the cube and get is simulating physics. So organize this. And we're going to plug in our return value to the branch, which in blueprint a branch is an if-else statement. If it is simulating physics, then it will go to true. If it is not simulating physics, it will go to false. And if you want to do an else-if statement, you would just create another branch and connect it to the false, and then so on and so on. And then the final false, which in our branch tree would be the else statement. So, out of the true, we're going to add impulse to our cube. And then what we're going to do is drag out of the impulse and use multiply by a float for vector times float. And our z is going to be +1. So it goes in the world up direction. And then we're going to drag in our jump strength and connect it to the float value. And this will cause our player to jump. And let's also check velocity change, so that way we don't have to worry about making the number very high like we did with hit strength, which the add impulse set location does not account for that within blueprint. Then out of this execution pin, we're going to draw a debug string. And for our text location, we're going to use the getActor location. And our text will be, "I'm happy to see you," and then a little smiley face maybe. Let's change the color to purple. Since we have the damage color being red, let's make this purple so we can easily see it. And the duration, let's set it to 2.5. Let's compile and save. And if we right click on event on interact, we won't have a parent function to call, since this is only within blueprint and it only inherits from actor, which the actor class does not have this interface implemented automatically. So here we're checking if it's simulating physics. If it is, then add an impulse where it jumps up, causing the cube to bounce. And then we draw a little message saying, "Hey, I'm happy to see you, nice to meet you." It's whatever you want, really. So we can save, and let's go back to our content browser and let's open up our MPC Interact blueprint, since we already placed our bouncing cube within the level. And in here, we're going to call the event on interact. And since this is blueprint only, we won't have to call a parent function. And out of the execution pin, we're going to set the actor rotation. And we're going to get our interactor actor, and we're going to get its actor location. And then we're going to get our actor location, which we can just actually duplicate this get actor location node, and it will automatically use our self, or this actor. Now, out of the new rotation for our set actor rotation, we're going to drag out of this and find look at rotation. And we're going to connect the return value for our actor to the start location, and the target actor that we want to look at is our interactor for our target location. Now when we interact with our actor, it's going to rotate this character, which is going to look at the player, but it's going to rotate all axes, which is going to be the X, Y, and Z axis, which we only want the Z axis to really rotate. So we can actually break the return value for either one by holding the Alt key and clicking, or right click and there should be an option to break the link. Now for the return value of our lookout rotation, we're going to right click and select split struct pin, because rotators are structs, and for our set actor rotation we're going to also split this struct. And we're only going to connect in the Z or yaw value because we only want it to just turn to our player, not to look down, which will cause it to clip to the ground, which is not what we want. And if you want a blur effect to occur, you can leave this unchecked. If you don't want a blur effect to occur when he rotates, you can just check the teleport physics. And then we're going to draw a debug string. as our hello message. And we're going to use our actor's location again for the text location. And the message is, I don't know, why hello there. And let's use the color purple as well for this one. And our duration we will set to 2.5. The reason why we don't have to put in a test base actor is because it really isn't important and it won't really affect it in any way. Let's compile and save. And now what we have in this actor is when we interact, we're going to get the look at rotation, and we're going to rotate our actor to look at the player, and then we're going to print a little message saying hello, or something representing that we identified that the player interacted with us, other than just the rotation. In the next video, we will be allowing the player to use our interaction system. Welcome to Section 6, Video 5, allowing the player to use our interaction system. In this video, we are going to allow our player to use the interaction system via a button press. So first what we're going to do is open up our Blueprints folder inside of the Gameplay Elements folder, Interactables, and we're going to open up our Door Interact BP, select our static mesh, and inside the static mesh, double click on SM Door, or the actual icon, to open it. And we don't have any collision for this static mesh, so we're just going to go to the collision tab in the top and add box simplified collision. And there we go. And if you can't see it, you can select collision and simple collision and it will show up. And let's save that. And we can close this. As well as our character, let's place him into the level, and let's reorient him by opening him up, and let's move him or rotate him 90 degrees. So -90, so he's facing the correct way. We can close these two tabs now, and let's add our character's functionality. Inside the C++ classes, in our characters folder, select our player character, and let's open that up. Inside of the header file under the protected category, we're going to add in a variable. Here we are declaring our interaction distance, which is how far we can reach to interact with something. Under the private category, we've added the interact function, which will handle calling onInteract for anything that is written within our interaction distance in front of us. We are going to bind this to our interact key action, which we set in the input setting of our project settings. Let's add our definition, and let's go into the source file. Inside of our constructor, we are just setting the default value of our interaction distance to 240 units. Inside of our setup player input component function, we are binding the interact action to our interact function for when the button is pressed. So inside of our interact function, the way we're going to interact with anything is by shooting a line trace similar to how we've done it before, by starting from our camera location and then in the forward direction of our camera at a distance of the interaction distance. Then we set up a struct to see if any collision objects are to be ignored, which will be the player, which is us, and then we fire the trace to see if we hit anything, and if we did hit something, then we save that hit actor, get its class, and check if it implements the interface, which is our interaction interface. If it does implement the interface, then we attempt to cast for it and save it within an if statement. If the cast succeeded, then we use the saved interface to call the onInteract function. If the cast failed, then we call a generic version of the function, which requires us to input the actor that we're calling it on. In both cases, we pass in this actor for the interactor. The reason for why we cast is because it's checking to see if the player's class inherits from the function in C++. If it's blueprint based, then we won't have it inherited from the interface since it fundamentally can't inherit from that. So we check for the C++ layer first. If it does implement it, then call that function since it can call the blueprint version as well, and this is because it is a blueprint native event function. Let's save all, and let's go back into Unreal and compile and test this. Now that we've finished compiling, let's test this by hitting the play button. Let's walk over to our door and hit the E key to interact. and it rotated 90 degrees, and if we hit it again, it rotates back. And as you can see in the output log at the bottom, it's printing out a message saying interaction called from player character, which is what we want when we call the player or parent function. And then if we interact with the cube, it bounces up and down and says it's happy to see us. And if we talk to the person, he looks at us, should be saying something. It's on the ground. My bad. That's why it's not showing up, because it was below us. So if you want to fix this, we can drag this in for our message location and get component or get world location, and use that as our text location. Compile, save, and then we play, we walk over to him, and he says it where his face is. In the next and final video, we'll be building our level and packaging our project for shipping. Welcome to Section 6, Video 6, building our level and packaging our project for shipping. In this video, we are going to build our level and package and test our project. First, we are going to build our level, but before we start, I invite you to pause the video and see if you would like to design your level again using these new gameplay elements that we've added. So now, to build our level, this is the process of generating lighting and geometry if this hasn't been done so already. In the top toolbar, where it says build, we can select this and it will automatically handle building the lighting and geometry for us, which may take a little while. In the drop-down panel, we have build lighting, and we can also select the lighting quality. If we want production, it will take the longest, but it will look the prettiest, that type of thing. Preview is what we're using now. Update reflection captures, which is something from our modes panel. And if we go into the visual effects, and we have planar reflection, box reflection, sphere reflection, we can place these into the level, like so, and they add a sort of prettiness to the level, which is such as reflections and such. So, we can also build geometry, build navigation paths for AI and such, build our LODs, texture streaming, etc. In this case, we're going to update our reflection captures, and then we're going to build our lighting. This may take a little while. Once it has finished that, just select build, so it handles building for everything. You usually want to build lighting first because it's going to give you errors and some things won't properly build because of that. So, now that it's finished building, select Save All, let's Save Selected, and now we're going to package our project. So if we go to the top left in File, and then Package Project, Windows, Windows 64-bit, and once you have selected your package location, it will take a while to package, but we're just going to set the location for our package project, which is specifically where you would like it on your computer. In this case, I'm going to place it in a folder called Builds, and then I'm going to make a new folder and name this Packed folder. And you should have a name under here, otherwise it won't work. So I'm going to select that folder, and now it's going to package for the project, which is going to take a little while. So pause the video, and when it finishes, resume the video. Once it has finished packaging our project or our game, let's go to the location of our packaged game. Let's open the folder that we placed it in, and it will show up with a name such as Windows No Editor or a general specific name that Unreal has to make for our packaged projects, which in this case for Windows it's going to be Windows without the editor, which is just without the Unreal Engine editor. So let's open that, and we'll have a bunch of files and folders and such. The only one we want to use for running our executable or game is the .exe or the application. So double click on that, and it should load up in full screen, which is what we have specified because that's the default for Unreal's package builds. You would have to specify in code if you want it to be in windowed and such. So let's actually test this. Let's select Start Game. Alright. We seem to be able to shoot. We can jump. We can sprint. I walk over to the explosive barrels, shoot them, and I take damage and they both get destroyed. I can pick up health. I can talk to our character here, who just says one thing. Our cube can bounce around and he says hello. We can also shoot him. We can open our door. And I placed our level ending actor next to this chair. and set the level to open the main menu. So it should open that, which it did. Let's start it again and test our pause menu by hitting the escape key or the backspace key. And it seems we can pause our game and resume it. Quit to main menu. Let's start the game, and let's quit to desktop via our pause menu. And it all seems to work. So in summary for this course, we've learned about the basics of C++, learned the basics of Unreal Engine 4 with C++, created our player character, added our gameplay elements, created our interaction system, and packaged and built our project. I hope you've enjoyed learning from this course. I've enjoyed teaching you how to code C++ within Unreal Engine 4, and I hope you have a wonderful day.